Sou o beijo no microfone. Não, eu vou pegar. Test. Můžeš zaspívat? Ne, nebudu zpívat. Jo. Pane, můžete tady představit? Jo, počkej, to docela jednou video. No. Vy jste včera vyprovoval ten kameru. Tu kameru nemusíte vypínat, dělat. Jenom tam dá. Jenom na tu zůmu. Jenom na tu zůmu. Jenom na tu zůmu. Yeah. No. Taky bude vaše ještě pan tady pokud se dějí
ale dělo toho kolegiu skoro. No, ale jenom když byste ustupovala, tak šlo se. Ale ty možnosti jsou...
Děti vidíte, že to bude tady, no?
Já bych byl pro, kdybychom tady udělali normální asanací pořádek s cedulkama a sedmi si zahájili. A když se pak ten, kdo bude vystupovat, tak bude tady hovořit, tak to zahájíme jako přehledně. Jo? Takže dáme tady od toho prvního. Takže pan Pavel Šmutala bohužel nebude, protože je mocnej a pan Minžel Macanauer mi včera poslal, že je také mocný. Tyhle dva ne.
A my to máme natáhnout, ten tiket.
On nás kolega Marek, já si neviděl na začátku a pak se vzdálí na chvíli, když je paralelně. To si vymarali na takovém vlastně na rozdíl ani smlouva ne. Ani
No? Halo, halo, zkouška zvuku. Pane Fuchs, slyšíte mě? Můžeme když tak teda zkusit angličtinu.
this is the English channel speaking. You are listening to the English interpretation on the English channel. We're at the Nuclear Days Conference.
Jo, jo, perfektní, tak zkusíme češtinu. Jo, jo, pořád dobrý. Děkuju.
Slyším pan Lecka, že jsem byl tak já se tu prezentaci nahrám. Já možná, já se to budu pomůžu.
Jo, to neměl být. Ale já budu jo, bude tady takhle na svým má vyčasky. Dělali jsme rozpočet. Já bych měla právě. A to jsme dělali, třeba tam bylo. To nemám, tak já když tam nejsem, tak tím pádem to nejbáví. A to ještě si musím říct, že to jsou takový. No to bude takový, že to nebude říct.
Společenství večer.
Ale nikde jako schovaný není.
Pití.
Já ti pomůžu.
Un braccio di tutto
Slyšíš tam něco? Ono to bude možná chvilku zpoždění. No tady je to blbý.
Můžete mi někdo říct, jestli jsem viděl.
Tak já se tam dostanu.
Jak se jdeš podívat. Uvidíš, když já. No to uvidíme, to uvidíme.
Když tady dál.
To dále, to není doma.
No, ať to někdy, no. Ale může rodinu na to dělat. Jestli vám to nejde dělat, ale je to ale těm krásné. Na to začátek to jsem rád.
Vypadá jako káva. Teď se má
Good morning, ladies and gentlemen. I'm glad to see you in a slightly smaller number, but still, you are here. Let me welcome you to day 2 of the Nuclear Days conference here in Pilsen. Yesterday's round table was dedicated to the energy crisis, both present and the future. And we were also asking ourselves the question how nuclear power could help us. Today, we are going to talk about how the nuclear energy sector can help, and we hope that it will be able to help also in the heat supply sector and the related industries. Without further ado, ladies and gentlemen, let me welcome the participants to today's round table. Unfortunately, 2 of them can't attend because of sickness. Mr. Pavel Shotola from the Ministry of Industry and Trade of the Czech Republic and Mr. Michal Macenauer, the Head of Strategy at EGU Brno from the Czech Republic. These 2 gentlemen unfortunately can't attend. So they apologize for not being able to attend. But I hope that we have a good representation of the other sectors and we have a great lineup of experts. Let me welcome Mrs. Silvana Jirotkova, the head of the SMR department at ČEZ, Mr. Jiří Vecka from the heat supply industry of the Czech Republic, Heat Supply Industry Association of the Czech Republic, I should say. Mr. Stepan Šmída, are you here? Yes, I'm sorry, I didn't see you because the gentleman was over there standing. I'm sorry. So, good to have you here. Mr. Stepan Šmída, head of Business Drivers Doosan Škoda Power, Pilsen, and Dr. Vladimír Wagner from the Academy of Sciences of the Czech Republic. Now, the host of this round table is nearing very swiftly, but he's not yet here because of some traffic jam issues. I will take the liberty of kicking off this round table for him and on his behalf. And I'd like to give the floor to Mrs. Silvana Jirotkova so that we have something to talk about by way of starting. You have the floor. Good morning, ladies and gentlemen. First of all, let me welcome you all and thank you for the invitation. I really appreciate it. I was here the last year. I was sat in the auditorium. I will certainly follow up on what my colleagues said yesterday, and I'll try to sound as positive as the gentleman who spoke before me. Although, having said that, the future is not as bright as we would wish for it to be. If we don't do the things that we plan to do at ČEZ, for instance, I don't think the future will be that bright. Now, I need to say that I'm not an expert on the heat supply industry, but I have the honor and pleasure of being able to develop small modular reactors within the ČEZ group, ČEZ AS. It's not just the ČEZ, the mother company, but also the other companies within the ČEZ group are planned to participate in the development of small modular reactors. Now, I don't know if I'm supposed to operate the clicker myself. Okay, I can see it. Yes, I hope it works. Just to put my talk into wider context, you heard from Mr. Apotsky yesterday. Obviously, he's involved with the Temelín nuclear power plant, and that's just 2 of the subsidiaries of the ČEZ group. Just to put you in the picture, and they are preparing big nuclear installations, and there is a department directly within the mother company, so not within a subsidiary, but it's here in the CEZ mother company, and it's the development of SMR department. That's the brand that we use as the name. So I have the honor of being at the head of this department, and this clearly indicates that Petr Závodský and myself have certain missions to fulfill within the group. And just the very fact that we work together within the group, we obviously use the knowledge and the skills and expertise of our colleagues from other nuclear power plants. Although they are a separate subsidiary, we work together. And it's great to have them on board. I don't know if Petr Závodský showed this yellowish graph yesterday. That actually shows the future that we're going to talk about, and it actually shows what will happen or what should happen in the next 3 decades if we continue in the business as usual, and if we have simply embraced the European agenda, the green agenda. Obviously, the pressure for decarbonization is worldwide. It's global. It's not just the European Union wants something. It's something that applies globally. So you can see the graph showing the individual units, the nuclear power plants, nuclear installations, and they will obviously be phased out, and they will need to be replaced at a certain moment in time in the 50s. And so the 2 greenish bands show the traditional installations. Then the Dukovany 5 unit is the light yellow color, and then the brown, sorry, the gray or black, shall we say, color marks the phasing out of coal and gas. So far as the plan, at least. Maybe things will change. Perhaps the European Union's policies in the gas sector will change. So far, it's not the case. So the plans we work with include also the idea of phasing out gas. And this graph shows that if we phase out these sources of energy and heat, and there's no way we can cover the need for heat supply demand as well as the electricity. I won't go into too much detail what are the parameters that went into this calculation and this model. There will be things like also synthetic fuel manufacturing or lines or production lines. These will need electricity as well, and these are not included. There's a whole lot of things that you can or do not have to use in these calculations. Our colleagues from other companies also did the same thing, and overall there will be a deficit of 30 to 50 terawatt hours per year. That is the outcome of this calculation. So ideally we would be building 4 nuclear power units, and still we would need 3,000 megawatt hours electric. And we plan to build the installations to cover this power demand in small modular reactors, depending how things go. And I will try to share with you one of the potential scenarios that I would like you to take as something that is just an indication, not really a plan that we will definitely stick to. It will depend on how things work, and we'll then just adjust the number of small modular reactors. So there's a lot to be worked on, all of us in this auditorium. The schools need to educate a lot of people. There'll be thousands of people that we will need to cover all the areas of various expertise, specialties, specialisms, various fields, not just the electrical engineering, but also mechanical engineering and a whole lot of other things. Not just the work itself, but also for managing these projects. There'll be a whole lot of them throughout the Czech Republic.
SMRs, it's an issue that we have been tackling since 2019 at CHES. It's not just the department that we created. Since 2019, we have been assessing and evaluating how to make use of the first atomic nuclear location when we started developing our small modular reactor pilot project. But now we are also investigating how to use and where to implement small modular reactors so that not only we can use it for power generation, but also for heat generation as well. Primarily, we focus on the locations that we already have in our portfolio for heat generation, and we have to move away from coal and use clean sources. When you have small modular reactors, hopefully we'll be more agile in implementing them. However, we won't be fast enough to move from coal to nuclear power. We are saying that we have up to 2030 to phase out coal. I think we'll get there sooner, bearing in mind the electricity prices, for example. But I am afraid that we will not make it in time to introduce and implement SMRs so that we can move swiftly from coal to nuclear power. So the transformation will be rather slow, not rapid. Here on the map, you can see not only our current existing locations, Temelín and Dukovany. When you look at Temelín, there is a green circle that you can see, which means it's our pilot location for an SMR project. For very simple, prosaic reasons, simply because we do have a nuclear source there already existing, working, operating. It's a location that is well established and investigated, mapped and identified. We continued our further surveys and assessments, which only confirmed that this is the perfect location for this SMR pilot project. As far as other locations are concerned, we had a look at our entire portfolio of coal power plants. However, of course, not all of these locations are suitable for an SMR project. We will have to continue assessment surveys and a lot of time to decide which locations will be ideal to implement an SMR technology. We have so far gathered and collected the historic data for all these locations, including geotechnical, seismic data, so that based on these, we could identify the locations with the highest potential for future development of SMR projects. At the moment, we're focusing mainly on Detmarovice in Ostrava region and Tušimice in northwestern Bohemia. So we have further 4 locations that are here in green, Brunerov, Ledvice, Melnik, which are sort of a backup scenario for us, just in case Tušimice or Detmarovice projects fail. One of them is very close. Brunerov is very close to Tušimice, so it's a very close location, so it's a logical choice. And also for geographical reasons, because there is an open pit mine nearby. You can see it with your naked eye, but it makes the location more complex to handle. This is why we decided to go for Tušimice first. We are conducting very detailed surveys and assessments, including seismic activity, geotechnology, geology, etc. But also we are investigating how the SMRs should be placed there so that it makes sense in the light of the location, in the light of productivity, efficiency, in the context of infrastructure available, and the heat that is generated there currently, whether it's feasible actually or economically viable for an SMR to take over these tasks. So these are the documents that we are working on that could be submitted for the EIA assessment. The first stage does not clearly indicate whether all these locations are proper and suitable. However, we are only now trying to map and identify the areas that need to be further assessed. This will happen this year in fall and next year in spring. Hopefully, we'll then get more certainty as to which locations are suitable for SMRs. Also, we have to bear in mind all the regulations and laws in place that we have to abide by. To close my presentation, I have selected this slide and I hopefully leave some time for questions. Here you can see a very dynamic, fast, speedy scenario that we have developed for implementing and commissioning SMRs for the maximum of 300 megawatts, approximately 9 to 12 units. For the community here, I think it's interesting to see not only what it might mean, how to build 4 big units and 10 small units in 4 different locations. Dukovany, Temelin, these are the 2 we already have operational, plus we'll have to open another because 3,000 megawatts for Tušimice, Temelin, Dukovany will not fit in to these 3 locations. This wouldn't be optimal. When you look at the lower part of the graph, the red lines, these are the 4 units, which represent one of possible scenarios for new MPPs. I think yesterday we had a number of presentations regarding the state energy concept framework, conceptual framework, etc. And this will be something that will affect actually the scenarios that we will apply to building these units. So this is not a dogmatic scenario that you see in front of you. It's rather some idea how we could go about it. So we would start with unit EDU 5, and then we would move up to the last unit EDU 6. If the decision is made to build these 4 large units, then this is the scenario we'll select. However, if there are some hiccups on the way, then we would opt for a number of small modular reactors, which would mean that all these green trains that you see in the upper part of the graph would be even expanded. Probably some of you might laugh at these plans because they seem overambitious. However, I think that we have so many representatives of academia and of the industry here. We have students. So I think it's a very positive picture of a potential future. Hopefully, you will all find jobs thanks to that in this industry, because the industry is very prospective and has a large export potential for the future. So it would not only be about the heating and heat generation, but also we would contribute to the development of the nuclear industry in the Czech Republic. We often say that we wish that our nuclear industry would actually win over in the competition against the automotive in the Czech Republic. Hopefully, let's keep fingers crossed this will happen, that the automotive will be overtaken by the nuclear generation in the Czech Republic. Thank you for your attention. Thank you to Ms. Jirotkova. I do apologize that I missed the beginning of our meeting today. I had some problems reaching this university. I got lost in the city center. I turned right to a one-way street, so I was in a lot of trouble today just getting here, but hopefully now it's all behind us, and I can take over moderation of this session. I have a number of questions to our panelists, and maybe we will leave it for the later part of this session, and maybe let's go through all the interventions first, and then we'll move to the questions, unless there are some comments that are urgent. If not, then let's move to the next intervention.
Good morning, ladies and gentlemen. Thanks very much for inviting me to this beautiful conference. This is my first time here. Did I hear you well that you said this is the 13th edition? Oh, wonderful. This is my first time anyway, and I'm really very pleasantly surprised that this is such a high-level, high-profile conference. I believe we can talk very openly. This is a sort of closed cloisters type of event, because we might be thinking about things that are not that usual. I'd like to tell you a bit about the Association of the Heat Supply Industry of the Czech Republic, probably the largest professional body in this sector. ČEZ is not our member, but we do cooperate. And I believe this is a sector that is really coordinated and consolidated in the Czech Republic. I'd like to talk to you about how we see the process of transformation of this industry in the Czech Republic until 2030 and beyond. And I will, of course, talk about the nuclear power perspective in it. I will start with Germany, which might be interesting, perhaps even weird to you, but our saying is that if it's good for Germany, it's good for Europe. So wherever Germany is moving, the European Commission will probably move towards. And one can see that the distance heating networks are gearing up in Germany. They have a target of increasing the number or proportion of connected households to 40% by 2045, which is the current number in the Czech Republic, by the way. I don't know how much time I have. I've got about 10 slides. Is that okay? So that we can spend some time discussing things. Okay. As regards the contribution of our industry to decarbonization, again, I don't know to what extent you are familiarized with the data for the Czech Republic. This is just a very brief, certainly the nutshell. Particularly, we're talking about low emission sources of energy, and typically, of course, it's going to be a nuclear reactor. So without using these in our industry, probably there's no way forward. What might be an option and an interesting route to take would be the use of waste incineration. We got 16.6 gigawatts of installed power and 6.6 in contracts, that's sort of in the pipeline. So if that works out, all that works out, it's really a crazy situation. So there's going to be a whole lot of overflows, and there could be a good use for them using heat pumps, perhaps, in the network. If this is not the case, then it'll be difficult to operate the system. Here is an outline of where we see our next development. I think there are three main functions: flexibility and buffering, of course. We're talking about accumulation as well. Accumulating electricity, of course, is an option, but accumulating heat is something that is technically well managed already. Unfortunately, not in this country, though. But you can integrate the surplus energy and heat by using what is known as sector coupling. Sector coupling is not just about electricity and gas. the heat should be there as well, and geothermal sources as well, and solar energy, of course. Could you please put this next slide up? Thank you. I can't seem to be able to operate the clicker. Mrs. Irotkova, who spoke before me, already said, and I fully support this, that our reality is going to hit us about 10 years earlier than we had originally assumed. This is a chart based on the data from June. Now, the figures will be slightly different. The figures for 27 might be slightly better. Maybe Mr. Matzenauer could tell us a bit more about this. It's unfortunate that he couldn't attend today. Anyway, it's very obvious that there will be a point in time when the prices of the emission vouchers will cross the line of the power base load there. If we realize that 1 megawatt hour generated in a coal power plant, very roughly speaking, well, if it is simply, if the emission voucher is more expensive than that megawatt hour produced in the traditional ways in the base load, then of course that doesn't make sense economically. They might be in the head market or the intraday market, but generally speaking, the electric power plants will be operated in a completely different way. And it's very clear that it's going to happen before 2030, probably before 2028. So the electric power plants can't just operate with business as usual type of approach. Of course, unless the government steps in with some kind of subsidies. Doesn't look like it at the moment. Here is an overview of the conditions for delivering a successful transformation of the heat supply industry. The paradox is that the energy crisis really bought us 2 more years of lifetime. However, transformation needs to continue if we are to survive. And there are certain new options of generating heat. Obviously, in the past, we were making heat using coal, which was very cheap at the time, not now. But the different price levels obviously allow you and require you to use different technologies, which wouldn't make sense in the old days, but they do now. In 2030, we will essentially phase out coal, and essentially it's before 2038, which is the deadline. It looks like the overall investment into transformation will be 180 billion Czech crowns. Of course, that estimate fluctuates. I originally thought it would be about 150. It's now 180 billion Czech crowns. We'll see how it goes, and it fluctuates. But definitely there need to be conditions in order for us to be able to deliver a successful transformation. So there needs to be reasonable legislation. There needs to be good support in terms of operating these facilities, and there should be some, let's say, more forthcoming approaches by the regulator. And of course, for us, talking about the economic side of things, we would need to make sure that the conditions are very similar to a level playing field compared to the conditions for renewables. As regards the Fit for 55, which is the main legislative framework, which is minus 55% of emission gases generation by 2030, from our point of view, it's not that bad. But the main thing would be the EU ETS, which is the legislation that essentially lays down the rules for trading emission vouchers. So emission trading essentially for up to 20 megawatts enjoys a special regime under ETS2. We definitely do support it. The question is how this works out politically, how this plays out on the political side of things, because we might be nearing the price point at which, let's say, the petrol at a gas station will be 2 crowns more expensive per liter. And the question is how our politicians will respond to it. But the plan is for the moment that by 2027, this will have been up and running. And from our point of view, creating a level playing field for all the players on the market is important. Also, upgrading and modernizing the gas sources, also a key thing by 2035. There's not too many opportunities and too many other options, by the way. If we need to phase out coal, what is the replacement? Probably gas, and pretty much gas only. Of course, it would be great to have the nuclear power plants, but we can't make them that quickly. ETS1, then it wouldn't be of much concern to us. But we don't have a problem with the price of carbon, but we want our competitors to pay the same prices. Maybe there could be a general universal carbon tax, but everybody needs to pay it.
The Renewables Directive is another legislation that we had to consider. It regulated the use of biomass, whether we can use wood pulp, which was actually facilitated by the Swedish presidency. The Swedes were very decisive about it and were fighting for it. And I'm really happy that we had them in our corner, because otherwise we would have failed. It's extremely important, especially in the light of the nuclear energy, this directive. Here at this slide, you can see some general overview. If we want to get some funding and benefits from the EU funds, for example, phasing out safeguards, etc., we have to have operational heat grids. For them to be operational according to the directive, we have to meet certain requirements that have to be met until a certain deadline. When you look at it from the perspective of heat generation, the directive defines the way the heat is generated. If it's a turbine that produces and generates both electricity and heat, then we are talking about a CHP generation, which means essentially that the heat is gradually decreasing and cannot be actually contributing as one of the parameters for deciding whether a grid is operational or not. So there is still some time period until 2040 we can account for CHP, but after that we have to have 95% of renewables, residual heat, and the combination, and the renewables have to be at least at the 35%. After 2045, essentially there won't be any CHP allowable or eligible for funding from the EU. So the heat could be produced in CHP, however, it may not be included as a part of the operational heat generation grid according to the EU directive. The same Renewables Directive it defines that this is heat that is not produced under CHP technology. But for example, if we take heat from the cooling towers, where the heat is produced and it is only produced as part of the process, but not, it is not our target, it is not this is not us producing it, it is not a cogeneration heating plant, but it's just somehow appearing or being generated or produced by the way, then this can be used under this directive. However, clean CHPs, no. France was opposing these the directive, but essentially the result is that there is some funding available for CO2 emissions when we're producing heat. So there are two different approaches here. One approach is that we are looking at the operability of a grid, or the other approach is the emission factors. And it can be also combined. So the directive enables for the combined approach to this. When we have a nuclear power plants, then the emission factors are met. However, the operability not so much. So it's important to remember that we have to follow these legislation requirements. Here we can see what is a high efficiency CHP. This is something that we can meet, which is 270 grams of CO2 for 1 kilowatt hour. So this is an effective way to produce heat that is well met by the NPP technology. Here we can see a modeling until 2050. When you see coal, natural gas, biomass, geothermal energy, and biomethane, we included only Dukovany and Temelin. We do not include in our modeling any planned SMR units. Should we get access to such data, we can remodel. We still are fighting, or we are faced with underfunding. Also, we have to remember that there are so many new provisions of law in the EU that have not been implemented here in the Czech Republic, that we are not sure how it will be transposed to our own national legal framework, which is another source of insecurity. For us, it's absolutely crucial to get access to funding from the HEAT program for remodeling and for refurbishment. It has not been released yet, this funding program, because of the ministry lagging behind in preparatory work. Hopefully, the Ministry of Environment will help us out here, although I am skeptical about it, but fingers crossed. As far as the operational support for CHPs, we have not made any progress here. We need to have steam gas installations in place, otherwise we won't get any operational support. The European Union is absolutely refusing to accept the rule of the relevant profit based on the ROA rentability of the assets. And there are many companies that have boilers under 20 megawatts that don't have to pay for any emissions, etc. So they're in a better position. Here you can see how we use heat from NPPs in Temelin and Dukovany. We use the Temelin plant to heat České Budějovice. Dukovany will be connected also to the heating plant, but no. If we had more NPPs, we would all be happy to use the heat from these plants. However, we have only the two, so these are just the only two locations that can make use of the heat. If the other units will be built, SMRs or be it other, we have to decide whether it will be 300 megawatts. It's not really small for heat generation, but we could make use to it, and we could make use of up to 300 megawatts for heating purposes as well. Even in that case, we will get 100 megawatts in heat. And of course, we have to prepare for legal changes, the changes in the legal framework, but this is a whole lot of other questions combined with this. Thank you. Thank you. From your presentation, one thing is clear. When we have too many laws and regulations, which is the case of heat generation, then when I think about employability in the heat generation, I think it's the most welcoming environment for lawyers, and the remaining 2% will be made of engineers who will be trying to get some heat into your central heating at home. So that's my comment to your presentation.
Good morning. Just like the gentleman who spoke before me, I am here for the first time, and I feel bad about it, I have to say, because I studied nuclear engineering, and in relation to what was said yesterday, I really believe I am part of the lost generation, because we studied nuclear engineering, and very, very few of us, having graduated, really stayed in the business. Some of us definitely made the decision to go out of this particular field after the Fukushima disaster. But I hope that this conference will shed some more optimistic light on our industry, and that students will become again interested in working in this field. I'm from Skoda, Dosan Skoda Power, and I believe that this is a counterpoint, if you like, to what we've done. Driver powers would be not something related to driving, but really we would be talking about something and taking care of something that you people from the nuclear power industry feel bad about. Would you feel to be a dirty word? We essentially are in the temporary sources of energy. So I'd like to shed some light on this and offer you a couple of new perspectives, perhaps. In the afternoon, there'll be a colleague speaking in way more detailed way about the steam turbines for modern nuclear power plant cycles. But let me say that we don't consider ourselves to be just a manufacturer of, or the leading manufacturer of the traditional, conventional turbines, but we do all other sort of things, depending on new coolants and new heat bearing media and that sort of things, because we need to go with the trends, we need to go with the flow in the energy sector. You've seen this yesterday, probably. Many people asked me, what was this about? What the heck was this container, this bluish container? What is it used for? It's a fuel cell providing 400 kilowatts of power, electric and thermal. The conversion rate being about 90%. This is nitrogen. So I think it's a good contribution to our debate about using or perhaps not using hydrogen in the heat industry. Then you heard the acronym SMR many times during this conference and elsewhere. So the small modular reactors we supply, and we work with a number of manufacturers and suppliers of these small modular reactors. We've come to the conclusion that some of these projects that we originally thought would work out well seem to be less viable than we originally thought, but we still provide a lot of support to this area of our work. Let's move on. First of all, talking about this whole context, we need to think about what the heat industry is about and what its transformation will bring about. We supply various consultancy services and support to traditional heat suppliers in the decarbonization effort. And primarily, whichever perspective you take, you end up with the answer that probably gas is the option to go for. Most people agree that gas will stay with us for another 15 years at least. Whether this will be through a port somewhere in Germany, or whether it will be through a terminal that is somewhere in the Netherlands on the sea, we don't know. One way or the other, it probably will be the case. The old heat supply companies used to be destined to the fate of providing heat and sometimes, in the peak hours perhaps, electricity. It was okay for them, sometimes less okay for them, less profitable, depending on the speed with which some companies have decided to deliver their own electricity and make their own supplies of heat and power. Sometimes the demand is not there, but still you are obliged to supply electricity to the network, very often at a price level that is very low. So some of our heat supply companies are really running into huge losses, particularly during the summer. So the question is to what extent we can make good use of our technology of the turbines in future projects. Very often it would be 50% of the project fund of operations, often or frequent output changes, output power changes, etc., etc. It really depends on how the heat supply companies want to go about their profitability and the revenues in general. If it's a classical turbine with a separable, disconnectable, low pressure unit, then you can supply at a regular rate, and then within minutes you can link up the low pressure part, and then of course you can go up in the output if ČEZ requires so in very short time. Generally, it is expected that machines will require better diagnostics, better levels of control, and there is a software that we use for this purpose and calculation and modeling. My colleague will speak about it in more detail, and there's a whole lot of new technologies that we can use on the whole cycles, not just the turbines proper, that will put us in a better situation, better position to calculate all things and model things. And are we able to respond to new developments? Oh yes, we can. The answer is yes, we can. There are sources of heat that have been around. Some of them may have been phased out. If I'm not mistaken, it's dozens or even hundreds of megawatts that these machines can provide in thermal energy without any major impact on this technology proper. Yes, of course, there will be a difference in the price performance ratio, shall we say. But if you talk about a nuclear power plant, and if it is requested to provide thermal energy, it's definitely not a problem from the technical point of view. Of course, you need to quantify your potential requirements and demands levels, because, you know, if EDU now finds out, well, it might have been good if we had thought about thermal energy as well. Well, if we do our math properly and think about things in advance, we can do it. I remember in Brno, they decided they would be actually working with completely gas, electricity, and now they might be actually really glad for the option to go gas, so to speak. Okay, here's an insight into, and that might be slightly controversial, what we can actually do in terms of improving the cycle. Are there any? Question mark. Mr. Vitska already outlined this. There is an option of using thermal pumps. In our perspective, we would actually use a different method of using the thermal pumps. These substitute the standard connection, a standard circuit of the standard heater and the peak heater. We do know that this would not work in traditional power plants, heat power plants, but for new plants, yes, we can talk about this option. The situation would be more difficult for certain installations, but you can use the heat from cooling the generator because it's got good potential. So there is a way to calculate this, whether this would be a viable option or not.
So here we would be at the 68 level, which for some might be really low, but these are very good pumps. Generally, it means one thing. You provide the same amount of heat, while at the same time you consume roughly 50% of the steam. The steam stays in the pump that can be reused for electricity generation. This is a solution that we implemented for one of power plants, which was 30.5 megawatts in thermal, and the rest was the electricity generation of the turbine. When you look at it from the heat generation point, there is a number of underlying prerequisites. We have to be very careful about backflow of the water. That has to be at least at 70, 80 degrees centigrade in order for it to make any sense. Probably this is a diagram that you know very well. This is a basic cycle for the installation. We have a turbine here with an extensive regeneration. We have a condenser. We have cogeneration. Then we have some pumps in this diagram. And it doesn't really matter whether there is a boiler or whether it's a nuclear reactor, because here it's all about the tanks with a liquid salt, which absorbs the excess surplus of electricity from the grid. If you want to have that kind of installation, then you need to have the saline tanks of at least 1,100 square meters, which is enormous. And this is loading 10 times 10. What I wanted to show here is that because of the steam, from the perspective of the steam cycle, it really doesn't matter what is at the top of this diagram. It can be renewables. We're not against renewables, but these are atomic days. So we think that nuclear power plant would be an optimum solution. And that's it for me. Thank you to Mr. Schmidt for his intervention. And now, Mr. Wagner, the floor is yours. The Czech Academy of Sciences. I will make use of the fact that I'm the last in line of the panelists, and the the last before the discussion, so I will try to somehow summarize what has been said and prepare the floor for the discussion. Let me talk about the use of nuclear heat, not only in heating, because there are some competitive uses of such heat, for example, for heat pumps or electricity. So I'd like to contribute to the topic of heat generation and heat supply. And also let me start or introduce the discussion. I know that our moderator has a number of questions to moderate the discussion, and he mainly wants to talk about small modular reactors, but I want to talk about the challenges ahead of NPP or nuclear energy. And one of the challenges is actually so that nuclear generation would also contribute to heat supplies, and how to make use of the SMRs. We believe that all the challenges that I have in mind are somehow connected and linked to the heat supply. Currently, globally, we have various options because of the situation that I would like to describe in brief. In the Czech Republic, probably we will buy some commercial SMRs somewhere in 2030s, possibly, even though we do have our own designs that are being developed. Nevertheless, it's quite possible that we will opt for foreign solutions in the area of SMRs. It has been stated a number of times yesterday and also today. Initially, our colleague here mentioned that Europe currently is in deep trouble. And we see also one thing. Even though we can't or won't be able to generate enough power, we will be in trouble because our neighbors will be in the same situation. They will not have enough power in winter because they don't have wind. There's no wind there or sun there. And in summer, it's even more difficult because we have problems with stability of the grid. When it comes to Temelin, which is an NPP, and we would like to use the heat from Temelin, then we would have to have a pipeline of at least 40 kilometers, which would mean huge heat losses. Here you see some graphs and images that represent everything that has been said. We are moving towards low emission technologies, but even if we talk about heat supply, we will have to move towards NPPs as well. You can see the situation in April, or when there is enough sun, and it's Germany. It's a graph about Germany when they were decommissioning nuclear power plants, and they only kept some fossil fuel plants. And in purple, you see the CO2 emissions. So as you can see, without NPPs, Germany will have real problems with power generation. Here you see the graph for August 2023. Even if they use only sun and there is not enough wind, so they do have to use fossil fuels to generate power. Same goes for France. So they do have to use in France NPPs together with renewables, which is the only way forward in heat supply and power generation. In France, they generate heat from electricity, and we know what's the situation in France in winter when the use of or consumption of power goes skyrocketing high. So here are the 5 challenges ahead of nuclear energy. We have to ensure that the running units are safe to operate and smoothly operational. We need them to have the longest lifetime possible, so that they survive until 2060 or maybe even longer. So this is the task ahead of us. And it is a task also for heat generation, because we'll have to use in Budějovice, the heat coming from Temelín. We do want that, and we want to take heat from Dukovany as well. The second challenge is the move or shift to third generation reactors. So there will be 1 or 4 new units, as we've heard from CEZ. These new units will also produce heat that can be used to heat and supply heat to České Budějovice or Brno, these 2 cities, or other cities as well. Third challenge is the introduction of small modular reactors. Possibly 10 such units will be commissioned, which would be great. And the development of the 4th generation reactor, that's the 4th challenge. And it's relevant for industrial type of heating. I'm not sure if it's applicable to high potent heat. Without it, our chemical factories or other big factories will not survive. So this is where the 4th generation reactors are important. And the 5th final challenge is how to heat industry. Nuclear energy can be used in heat supply, for heating supply, and for industry. This is the 2 areas where we should be able to use heat coming from NPPs, and this would ensure the low emission industry. How can we go about it? We can go the French way, where we use electricity to heat, and it also can be regulated properly, which means we can put the electricity in some heat accumulators and pre-generate the heat that can stay there for some time or be accumulated in these tanks for some time. This is one way how to go about it. Also, we talk about the necessity to use heat pumps. A lot of households opted for that, which means also the increased consumption of electricity, which is where the NPPs will be irreplaceable. Cogeneration for big units, that's another solution. There have been presentations about it. We talked about the heat pipeline from Temelín. There are some plans and designs for Dukovany, a number of projects in Russia and China that would generate heat for chemical plants and other industries where the need for heat is much, much higher.
And then the next thing we're going to talk about will be the use of small modular reactors, both for CHP cogeneration or purely thermal units. I'll go back in a moment to one that is already being built, and we can already collect some lessons in terms of the economic performance in comparison to the large units. And then the heat for industry. The use of the currently operated reactors, for instance, the Chinese reactor that does it directly for the Chinese chemical factories located nearby. The next option would be using small modular reactors and also other installations. There is an example of one Chinese installation that is already up and running. It is not as a priority the high potent thermal installation. It's meant to be a highly potent source of energy, but in principle, it allows to provide industrial use of highly potent thermal energy. And then we come to gas and all sorts of our gases, in fact, including hydrogen. Obviously, nuclear installations can be, particularly the highly potent thermal reactors, can be sources of hydrogen. So one can use this type of installation for regulating electricity, probably better use for CHP, cogeneration of heat and power. There is actually a heat pipeline from Temelín to České Budějovice, the major city in South Bohemia, near the power plant. And it would be great if these things could replace the traditional coal power plants and coal heat plants. And we are really being very optimistic with some of the programs, with the timeline being 10 years from now. But then again, it's, I think, reasonable to say that it wouldn't make much sense to use so many small modular reactors in the Czech Republic. We do need one, of course, to train our people on it, and then about a dozen, let's say, of these, as you mentioned, because once it is, let's say, the count of 10 or let's say a dozen, then it starts to make sense economically, although our companies can, of course, manufacture and develop small modular reactors for other countries, for neighboring countries, for the whole of Europe, when you think of it. But there needs to be a reasonable potential for it in our country as well. So small modular reactors could be one of the options that could contribute to heat supply. So far, they've been in operation only in Russia and China. And in most cases, they are very specific in terms of how they are being operated and what sort of units they are. And coming back to China, there is the traditional style of small modular reactor, which is probably the kind that we could use here as well. Then there are numerous projects still on paper, although in a rather advanced stage of licensing, etc., etc. And importantly, in the past few years, many companies that represent the dominant players on the nuclear power market sort of took the hint that small modular reactors might be a viable option, because our recent experience in Europe, wherever you go, has shown that we are going to need nuclear power. So the big players realized, okay, this is an option, there's a niche on the market, and they went in this direction. So EDF and Korean colleagues and also other countries, Holtec and all the companies, started to work on small modular reactors. Prior to that, they had been saying, well, okay, it is an option, but we'll see, and we will do it one day. But they have really started to do things now. So that's the kind of thing. We know that the Research Institute also is working in the Czech Republic, is also working on it. So it's quite fitting. ACP 100 is the small modular reactor that is meant to be completed by 2026. As of July 2023, they have completed. They completed the core module, and my take on it would be, well, yes, China, they have different approach to the economic modeling. We have a completely different approach to it. But the other thing is that if the small modular reactors work out well in China, the proportion between small modular reactors and the big ones, traditional ones, could be similar to us. And if it works in China, they find out that it works, and they start to deliver big numbers in series, big series of these small modular reactors for their territories, then it would be a signal for us that this could be a viable option. Although we are not going to buy this Chinese small modular reactor, it is still an important project that will provide some signal to us as well. And in closing, to give you one of the examples of the already operating high temperature reactor. This is cooled with helium, and The Institute of Research, Nuclear Research in Rzesz already works on this as well, and it would be very good to watch out for the developments in this field, see what the economic side of it works, if it plays out well, and if China is going to decide to build another one, then if they do, that might be an indication that that sort of equipment could be also used here in the Czech Republic. So that's it, and I believe this is a good kick-off, talking about all the papers you've heard so far, to our discussion about using heat and also using this for generation of heat, high potent thermal energy. All right, thanks to Lada Wagner for his surprisingly short presentation, given his habit of talking for a very long time in detail. And before you can ask your questions, ladies and gentlemen, I will take the liberty of summarizing what has been said so far. So, the decision about the SMR concept, most of what has been the content of our talks has been light water reactors. I don't need to comment on that, I don't think. The other options would be difficult to imagine in large-scale uses. So this is just to make sure that we take this into consideration. Modularity and optimum output for the requested purpose, that's important. That's an important one for me. I think there would need to be 2 units because it'll be a backup type of facility for the heat supply system. So if you wanted to comment on this, you're very welcome to do it. It might be a worthwhile comment to make. And then an interesting issue is the one of licensing. So far, there's a new scale, the American system, or the technical design. The base technical design has been licensed. I think it cost about $2 billion. And the documentation on paper added up to several tons of documents. Just to write this up took a bit of doing, to put it mildly. So I'm a little skeptical about this. I think we need to filter our expectations through this kind of experience of having to go through the licensing process. The option of building at the current locations, Silvana already talked about this. It does depend really where you are building. Yes, the rock, the bedrock, and all the rest of it, the geological conditions. There is actually one option, one question that comes to mind, and that is the one of economic competition. If we are really to fulfill the crazy expectations and crazy ideas of renewables being used in huge fields covered with solar panels, then we are going to need a lot of backups. But it's a matter for CEZ to decide on. And the issue is whether the heat and gas, the steam gas turbine will win, or a small modular reactor as an option. So it's very reasonable to think about the link up to the heat supply system, but we don't really know for sure whether a particular location might be out of the equation, out of consideration, simply because it is a nuclear facility and thereby the danger of contamination is larger.
And of course, we do have some deadlines that we have to follow, and I really appreciate that CEZ has their own agenda, their own planning and deadlines. I'm not sure whether you said it directly yourself or was it somebody else who said that there is a plan for commissioning and building SMRs, and it will happen only once we have a supplier who will be licensed, a licensed supplier who will be able to provide a technology that will be a turnkey kind of technology. They will build it and commission it. And I think that if we talk about the time frame of 2030, 32, I think we're being over optimistic. Another issue are capex and everything connected therewith. Very often we hear that SMRs are a fantastic solution, that you will bring something, they will just put it all together on site and it costs you nothing. And this is what we hear in the media. They can do that, of course. However, but a module for 77 megawatts in electrical, it is 60 ton. It is a 60-ton toy. I don't think that I think when we talk about 1,000 and 1,500 megawatt reactor, they don't weigh. They're not heavier than that. That you don't get heavier than that. So the entire module that the supplier brings in and can be commissioned, this is what it costs. And of course, we have to think about the costs as well. When we were initially talking about this project, these prices were fantastic, wonderful, but now the prices went up and they are not really much more economic than the large reactors. So you have to always balance the wins and losses in such projects so that we don't exceed reasonable capex. So it's very important to count the capex for a power unit, not for the entire installation. And we've heard in the presentation from the Heat Generation Association of the Czech Republic some hints of that that there are some issues connected with connecting the SMR to the heat installation. Is it something that is part of the tender procedure, or is it something that is only addressed once we define the location where the SMR is? So we have to think about balancing the grid flows. We have to think about steam generation in place in the location. So there are a lot of issues when we are talking about SMRs under development. And I think that we have 3 conceptual documents and designs from Rzesz, from Chevelte, and another facility in the Czech Republic who have prepared already their own design. So if anybody knows anything from our panelists about it, please shed some light on this issue. I think we have to also ask Czechs whether they are considering using the Czech design for SMRs that are underway, because of course I think that of course if we compare it with Rolls-Royce or Korean designs, we are not as advanced in our design as their designs here in the Czech Republic. So probably that might be an issue, but this is a question addressed to Czechs. And if our distinguished panelists could somehow address these questions, now it's the time. Just in a few sentences, if you could give us some feedback to the issues and problematic areas that I just mentioned, and then there will be time to take questions from our audience. I'll stand up so you can see me better. Thank you for your questions, but I'm not sure that I'll provide the answer just in a few sentences. All these questions and areas, issues, which you mentioned are very relevant. But let's take it from the top. Everything you asked about, or all the areas that you mentioned. Yes. Water pressure 6 times 1 boiler reactor. So we are in negotiations with 7 potential business partners here, potential suppliers, with 1 BWR, and everything else will be LWR. As far as the heat generation is concerned, I leave it to my colleagues. We will have 2 units per location. This is a must. We were investigating Dietmarice, Tuchačovice, and these are the locations that we're investigating, and they can take actually more than 2 units because it's 100 hectares, for example. So we are able to place more units there. However, we don't think it's very an effective use of location. So we'll only make use of a location until it makes sense in terms of heat generation and the use of sources in the location. These are northern parts of the Czech Republic, very industrial. So we believe that there will be consumers interested in our supplies from the industry. And so we need to also ensure the consumption of everything that we produce, be it heat or be it electricity. The locations, just like Temelín and Dukovany, are being assessed as to the transportation or transportation network. These locations are different geographically. There's a number of investments that will have to be made in time. We have different designs. Sometimes there is a scenario with road transportation, some account for other options or a combined transportation. So we have to remember that we have different locations, and we have to also assess and evaluate which transportation method will be the best. So we're preparing an envelope of requirements, terms and conditions, which include also a transportation mode for the future. As far as the schedule is concerned, yes, 2032 is a very ambitious goal, even for Temelín, but we did it on purpose. There is a huge momentum at the moment, and there is a very good atmosphere for actually going very strong about these projects. So the future is here, and I think it is time to put our foot down. We have to make use of the situation where the companies are being more favorable to nuclear power. This is why we're so ambitious. This is why we're trying to do everything to be as close to 2032 as possible. In these 2 new locations, the locations that I mentioned, the new NPPs, the target here is 2035. Because we still need at least 5 years of evaluation, assessment, and service, so we know where we are going to place our SMRs. So it's definitely not going to be any sooner. I don't want to tackle the price. I think what you said about pricing was correct. It's the unit price is important. The suppliers that we are negotiating with, they're not able to provide the unit price because they don't have contracts, they don't have documentation that could be used for preparing cost estimates or price estimates. But we believe that we can have or get the same pricing as for large units, but I think it all depends on the number of small reactors that will be commissioned. And the first ones will be, of course, very expensive. And the last ones won't be as expensive, will actually balance the capexes. For us, of course, the Czech Republic is the priority. Here we want to provide and supply heat and electricity, but we do want to think globally. We want to take nuclear sector to a higher level to make use of their potential. We are looking at companies who are interested in any kind of partnership, for example, in a joint venture format, so that we as ČEZ or ČEZ Group could contribute not only to the development of certain designs, but also to its installation commissioning globally. We don't have any parameters or limits to geographically which markers that would apply to. It won't be just 10 units essentially in the end, but we are looking at dozens of such units in cooperation with our partners. And this brings me back to the pricing, which means that with time, the price will be actually economical. So we won't be reliable on public funding. Of course, there is a discussion about how to set the pricing for the end users so that it's bearable or viable or payable even. This is everything on the table. We're discussing it so that we as chairs together with our partner can or are interested in investing it using also the state funding of the state where the partner is.
This brings us to the issue of partners. Thank you very much for, I don't know if it was a pass, playing the ball in this direction. Yes, we want to build one on the Czech territory, but if we want to get close to 2032, we might be first of a kind and number two, in fact, and after a very short period of time. So we would be building in the country of origin, so to speak, in the partner's country, and we would be building pretty shortly, probably a second first of its kind in the Czech Republic. So it's just to illustrate what plans we have in store for you. If we don't do it, we can't really meet the deadlines, use the small modular reactors by the mid-30s. And second, we would not be able to capitalize on the potential that is there on the market. Companies do want to invest in there. They are really considering this option. And the first ones who go in that direction will have the competitive advantage because they'll be able to cover the biggest demand, and that's a global one. And I'll stop there because I could talk forever. If I can chip in with my perspective on the heat supply side of things, I'm not an expert on nuclear power, of course, as you are. But in fact, it rolls back to something that I've already mentioned in my presentation. The heat supply networks are able to absorb a lot of impacts, and they can be used for all sorts of things. It's true to say that the current heat supply systems with the top temperature of 130 degrees Celsius, including reducing the backflow water temperature, that's the kind of thing that probably will be the case, but the idea is that the user would actually cool down the backflow water more in their heat exchanger than they are doing now. But the use of heat pumps is then limited by definition. I don't know if you know the physics of it, but there's a very big change. Certain types of coolants will be banned, and CO2 and other things need really low temperature backflow water. But things should be improving. So the majority of installations that we know of should not have a problem because you can use pretty much anything for cooling. It's essentially also the heat from cogeneration, combined heat and power. So the heat supply networks are suitable for that. And as regards the capital expenditure, let me say that the European Union doesn't say it needs to be this or that. It needs to be sustainable. So there are many more options open. We need to talk about the taxonomy as well. Will the heat generated by nuclear reactors be eligible? Nobody can say at the moment. We don't know. So if there are, I don't know, some kinds of special things and crazy filters for corium, whatever, particles, then, if we don't know what that will be, what this requirement will be, whether this requirement will be the case, then we can't make any calculations. So we'll see how things go, but we can provide heat at the maximum level, and we definitely support use of heat locally. The smaller the better, in fact, would be in our take on it. If we're talking about 500 megawatt installations thermal, they need to go down 8 or 10 times in the summer. Then it really depends on what exactly is it that you want to cover using the nuclear reactor. We probably would think about a base load, one machine, and then the intermediary period, and then you would need some kind of boilers to cover the peaks. Of course, that will be reflected in the economics. But that is something that we can simply model and calculate, and we can work with it. There might be also other sources of heat. If you compare it, for instance, with wastewater treatment plants, etc., etc., I believe the nuclear power plants are much better placed for the use of heat. So I don't know what else I should say, what else I should do in terms of supporting the ideas, because we know the Ministry in Trade and Industry is talking about this a lot. So we are saying in this message that we are ready to help. I haven't mentioned one thing. The energy sector is also, on the industry side of things, is also represented in our membership. So small units may be a sensible option. The question is how this plays out in combination with their decarbonization plans. But they still should be able to make it time-wise. Although it depends, let me say. the European Steelmaking Industry Association, now say that it is possible to decarbonize by 2050, perhaps even 2045, because I believe there is a hydrogen-powered forge and steel making plant somewhere, if I'm not mistaken. So this goes back to what you said. If we want to keep the industry, at least the chemical and these sort of industries will use at least 30 terawatt hours. If we want to maintain that industry, you know, certain people at the ministry level would tell you that this kind of industry will simply cease to exist in our country. So it depends on what we want. But certainly we need to make sure that we comply with the taxonomy requirements so that heat can be used in the EDT, but also ESG agenda will need to be taken into consideration. The environmental, social, and governance aspects will need to be taken into consideration, whether in deciding whether this can be used for the purpose. But certainly I can tell you that the heat supply industry will be very happy to cooperate. If you don't mind, I will only respond to some of the points that you brought up, because I'm not an expert on the rest. Licensing, that was number 3 on your list. I'd like to ask if somebody knows a bit more than that. Does Europe even have an authority that can license these reactors, or is it the case that it's just a very few companies and the United States? So the question is, does Europe have the capacity to license these reactors, or is it only American companies and American regulators, American authorities? Does anybody have an idea? I don't think that's an issue that we should be dealing with at this forum. The national regulator is required to have the authority to do it, to license, but the question is, do we have the people? And do we have the knowledge? Well, yes, okay, let me rephrase my question. Do we have the knowledge and do we have the people? Well, yes, there is a problem, because unless you require that the authority should actually license this kind of thing, then they don't have the people, they don't have the knowledge. So physically speaking, they don't have the institute doesn't have the people and the skills. Okay, that was my question. Okay, thank you for answering that. And then the decision on this concept, this is in line with the list of the planned locations. From the technical point of view, I understand that PWR and water pressure reactors. Sorry, would you mind talking about your particular perspective? I'm sorry, we can't hear the question. The gentleman was speaking without a microphone. Yes, I want to just do that first kickoff round so that we have time for questions from the auditorium. Okay, the last points on your list are certainly concerning us, and we talk about the procedure of design, the concept, and we are talking about the concept level discussions, not about particular locations and particular need for a certain technical solution, but the need or the modeling and design for a particular type of location then can be done really reasonably fast, regardless of whether it's a 100 or 160 or whatever megawatt reactor. So we are ready to respond to it. We are ready to help. It's always a matter of talks between the investor and the future operator. If it is a flexible type of installation, we can do it. Obviously, there are some limits, but you need to find the right intersection of the requirement between the electricity output and perhaps something else.
I'll keep it short so that we have enough time to take questions from the audience. I believe that when we talk about SMRs and count the capex against the output, this is not something extraordinary. I think that in the context of the Czech Republic, where we have locations for large units, we should build large units. SMRs are needed only in locations where there are some specific requirements for heat and electricity supply. And this is the rationale that we should follow when we are selecting SMRs for the cogeneration purposes or for heat supplies, so that it would fit into the requirement and the specifics of our Czech environment. So I believe that SMRs can fit in there, but we have to remember that the SMRs are usually meant for being built in a series, not in singles. And I think these are the models that are relevant for the US, where we have this investor-developer cooperation for building the sets of SMRs. But I don't think that it's actually relevant for the Czech Republic, where the SMRs are supposed to provide also heat and electricity in a very specific location where it would be a substitute for coal power plants. When I look at some of these models, I think some of them are very beneficial because they use one module as a two-reactor combination, and together we will get, let's say, 300 megawatts, but they can work in turns, for example, when there are two. And also, this is a way how to shift from a very effective power generation to a very effective heat generation, depending on the time of the year and depending on the needs. So I think that these are the models relevant for the Czech Republic, and they don't have to be even less expensive than large units. However, in the light of the entire life cycle of the project and of the use, we can count on the better efficiency of such units when we look at Temelin, it's just too large. We have to invest in long pipelines. So I think there are different factors that have to be taken into account when thinking about the viability of individual projects. Thank you. And now the floor is yours for questions. Thank you. Question at Mr. Vecek. When we're talking about the heat water pipeline at Temelin, depending on where we stand there, is it is according to the directives, but I believe that it would be the tertiary circuit, and we would have to somehow also mitigate the surplus of heat from the NPP. This is why we need a tertiary circuit, and this is why it makes it difficult to apply intermally. No, I think it's a high efficient CHP heat. It's not residual heat. The heat plant in České Budějovice, I don't know if there's anybody from this city, but as far as I know, there is a specific plan for this installation, and they have a biomass source in the central part of the heat generation plant, and it will be now changed to a burning house, and partially they will be connected to the 800 kilojoules from Temelin. What I believe is the case of Temelin, this is a highly efficient heat generation. As far as the efficiency of the grid is concerned, we have deadlines until 2040 to remodel and change the grid, including the renewables and other sources of energy. But the grid that we have there, I think, is very well designed, and I think it will make sense in the light of the legal changes. And I think also it's been something that we've been emphasizing for some time now, that it would make sense to have such an installation there in Temelin. And this is something that should be factored in when you are building new units, which is, of course, not the case of Temelin or Dukovany, because that's a done deal. I'm not really sure what you're asking me about, because I'm not very technically oriented in this issue. I could answer to any questions regarding laws and regulations on the matter. I have two questions. First one to Ms. Jirotkova. You talked about the support for the Czech industry and export. Does this mean that ČEZ is planning to support Czech industry by using Czech design for a nuclear unit and export it, or the other way around? Are you also planning to use a nuclear source for heating? And that's a question to Mr. Vecek. The option when the ČEZ is the subcontractor for a foreign design, it's not an option. We don't want to be a subcontractor. We want to be a partner. It would be a partnership where we would deliver, for example, development and production, manufacturing, etc. We have a lot of options and activities and operations in our group. And in a partnership, ČEZ would supply together with a partner SMRs abroad, using the supply chain not only within the ČEZ group, but also in the Czech Republic. So we would find partners in the nuclear power sector in the Czech Republic and use them as the primary suppliers for technologies in the SMRs that would be exported outside the Czech Republic. So that would increase manufacturing capacities, development capacities, and we believe that the Czech supply chain is not sufficient to cover the whole world, so you'd have to invest into manufacturing capacities. That would require a very extensive strategy planning, scaling up for the manufacturing in various regions in the world. This all has to be calculated, estimated, and agreed upon with our partners. But this is one of the scenarios that we are now developing. We do have Czech designs in our group. We are monitoring them. We are keeping our fingers crossed to our colleagues. The Czech designs are not advanced and mature enough for us to make use of them or to use them or to implement them in 2030. They're being developed, they're being worked on. However, the know-how and expertise used for generating these designs can be used in any kind of a modular reactor in future. Czech nuclear company. My question goes to Ms. Jirotkova. Does ČEZ think about building an SMR in Mělník, which is a small town near Prague? Yes, but there was also another question that I was asked, so if I could refer to that. If we want to operate a nuclear power source as a heating company, when we're talking about the standard units, this is beyond our scope. This is nothing we can deliver. But if we are talking about SMRs or other smaller units, then it's up for discussion, and we have to think and discuss whether regulatory authorities will set the conditions and requirements that will be viable and feasible and doable for us. If they will be the same as for large units, then we cannot commission any such unit. However, if the requirements will be less strict, then we can also ponder or entertain the idea of actually having our own NPP. It all then depends on the location. It doesn't make any sense to go to Dukovany or to Temelín. I'm not sure where are other locations that we could use to build a standard unit, but if we decide to go for SMRs, then it's a different matter. There is a discussion ongoing with regulatory authority or with the Ministry of Industry and Commerce, but nobody was able to give us a clear answer whether the requirements for SMRs will be similar to large units. So let me reiterate. Should the SMRs be subject to less strict requirements, regulatory requirements, since it is a smaller kind of installation, then I think it would be reasonable to loosen up the requirements. Then we might think about it. But there is a chance that the regulatory authority would say that it's the same kind of technology, so the requirements should be the same. So there is no clear answer for now. Unless the regulatory requirements for SMRs are loosened up, we cannot go and invest in SMRs on our own.
Hello, Vladimir Wagner is trying to ask a question. I'd like to just specify or clarify one thing. Certainly there is a handover point. Up until a certain point, it is a nuclear installation. And starting from that point, it is something that can be operated by a heat supply company. It's up to the investor. Whether the company is named the heat supply company in Detmarovice or Opatovice, it doesn't really matter. It's the same kind of licensing process. Well, yes, but it's important to mention that the operator, the company that operates the facility, needs to be licensed. We mentioned the issue of licensing. That's one, of course, but second, the operator needs to be licensed and needs to fulfill the conditions that are imposed on operators of these kinds of facilities. So that's going to be really dependent on how the design is approached and how it is built. Of course, you can license, based on the current law about nuclear facilities, you can actually license a reactor right in the center of Prague. You know, I'll give you a very good example. There are 2 reactors in operation here, the faculty of nuclear engineering. But if the first prototype block, the prototype unit in Temelín is built, and then it is licensed, and then this is something that is transferable from one location to another. And it doesn't have to mean that it will be a reduced number of pages of documents, but it'll be the same pages, in fact. And if there is general agreement that it is transferable from one location to another, then the rest will just follow suit. So it doesn't have to be a completely different type of licensing, if you know what I mean. But the first units that will have been built in the Czech Republic and elsewhere in Europe will show us whether it is transferable or not. If it is transferable, then this is how it's going to work. I already talked about it, but maybe it's good to reiterate. Yes, the Mělník location is an interesting one. Of course, there might be a competition of projects with a particular location. It's simply because we can't make the shift from coal to nuclear power in good time. So we are being very careful about making sure that the projects are not competing with one another. Dětmarovice and Tušimice, small modular reactors would be a priority for us, I dare say. So these projects that are currently in the pipeline might be sort of parked away and put on hold, seeing whether the small modular reactors will play out well. And of course, there needs to be a host of factors that need to play into each other. What is the location like? What are the facilities elsewhere and nearby, etc., etc. My personal view is that the Mělník location is attractive, and it probably will see some kind of development, but probably not now, probably in the 2040s. Once we have tested and test operated the other locations, then probably Mělník would see a small modular reactor. Thank you. Next question. I'd like to congratulate ČEZ on developing a separate department for SMR development. And I want to congratulate you as the head of the department. I'm glad that it happened. But I am afraid, talking about ČEZ, that ČEZ is lagging behind development. In 2011, already in 2011, the Nuclear Research Institute in Řeš, together with the Faculty of Nuclear Engineering at the Czech Technical University, already published the first study of using small modular reactors for industry purposes. There was another study that was made by the same 2 institutions for the representatives of the industry. And this project even led to a regular conference on SMRs between 2015 to 2022. There's an annual conference, and the conference deals with nothing else but the SMRs. Because of the delay that ČEZ had in jumping on the bandwagon, so to speak, it's unfortunate that Estonia, Poland, and other countries are ahead of us. ČEZ has simply not followed the trends in good time. And also, one more note, if I May, there are 11 projects that ČEZ is trying to develop. In my view, that's way too many. Some of them have been already earmarked as suitable by the industry, but that's just a side note. And on your question, Mr. Marek, at the level of Euratom and in the European Commission, I believe there are measures being put in practice for straightforwarding and streamlining the process of SMR licensing and putting them in operation, commissioning. And it's just side notes. And thank you very much, and congratulations, and all the best in your work. Thank you. Well, yes, this essentially is alignment of the license processes. That's something you expect also with the large projects. Hello, my name is Basdera. I'd like to ask you a question concerning the Heat Supply Association. The heat supply industry problems have been sort of long-term issues because that simply is something that goes back to history. ČEZ can actually do good work of a good job of combining heat and electricity generation. But what other heat supply companies and groups will do in this respect? That's a question. I don't know. One of them operates in Slovakia, and the rest, I have no idea. Is it really a technical problem? I don't see any technical problem. The problem is that the heat supply industry is a monopoly industry, a monopoly situation in small regions. And in order for us to be able to deliver a solution, we would need larger areas covered, and we would need some kind of concentration. I don't think concentration happening anytime soon because there are no conditions to it. So it will probably be, any development in this field will probably be hinging on our ability to get some subsidies and grants from the European Union. Because I think concentration is what we lack. We don't have concentration of players, that's the main problem, of facilities. And second, the problem in České Budějovice and ČEZ would be, you are essentially losing the regulated profit if you buy heat from that particular facility. So that's probably another reason why we have big problems in the heat supply industry on this side of fence. So am I right in thinking this is the case? Well, first of all, thank you for the question. I think it's not just a one question. I think that you mentioned several points that will be worth developing. When you mentioned a nuclear power plant in Mochovce, yes, the Noche Holding actually completed the site there. It was a sad site. So to be honest, I don't know if you've ever been to a place where they are building a nuclear power plant. That's really, really a big thing. It was before they brought in the fuel, so it wasn't a nuclear facility in operation as yet when I was there. Interesting stuff. As the Heat Supply Association, we committed to leaving or phasing out coal 8 years earlier than the European Commission committed itself to. And by the way, none of the conditions there has been met. So 2038 in theory is really just a theory. But we already work towards that aim in individual locations and with individual installations. Generally, the answer is, well, our clients, our customers don't want to pay through their nose for heat we supply. They just want it cheap. So 80% of coal and 20% of gas was the answer up until recently. If you want very expensive and not stable heat, of course, we can offer many other options. Then the issue of regulation as such, we get completely regulated by the regulator. And whatever we want to change in the network will need to be in line with the regulator's rules. Many countries to the west of our country don't have even any regulation in that at that level of heat supply. Sorry, I just finished this one and that got carried away. At the level of networks, you can switch off simply and disconnect under certain conditions when it makes sense. But what we do get to see is that there are certain processes that actually would not be allowed in the Czech Republic's legislation. But we want to be proactive. As you mentioned, concentration, we actually do believe that our networks are really highly concentrated. For instance, Copenhagen or Denmark or Stockholm, sometimes also in Sweden, I think they have even bigger networks. But Mělník, that's a lovely heat supply network. But certainly this is up for discussion. We can talk about this during a coffee break. Thank you.
One final question, please.
First one is for Syria, in your slide number 5, you mentioned 2036, Vietnam, Syria, and in parallel in your slide. Think about how many labor need for 3 large data, at least you need 12,000 labor skilled people. Where coming is 12,000 skilled people from Czechoslovakia. This is not question. I have talked very quickly, and not what the students are in food technology and not what. Second statement, the overnight cost 1 to 10,000 meters from ATR PM from China. Secondly, 8,000 if you with 80, maybe 5,000 down. But we have only 4 meters for it. But you use SMR for heating. Very expensive SMR, electricity, and we need heating. Is economically available? Economically? Give you 100 megawatt, $1 million cost SMR, and then you make generate at least 100 megawatt only, and then somehow you use it for heating. Heat generation. I think this is the, I cannot understand it for some plus minus almost points. Therefore, very good SMR, but SMR is very expensive. There is more than 2.5 times than last year. It is my question. The answer is translated for you.
Thank you for these 2 comments and questions. The price currently is it is of course relevant. We have to think about the pricing, but we only think about pricing once we have secured supplies of power. Small modular reactors primarily will not be used for a heat generation. It should be a side effect of their operation. This is not the primary target when we are building SMRs, but we are choosing locations where the heat would be consumed as well. When we have SMRs, they will be used for heat generation in a long time in future. It won't be sooner than 2035 in certain locations, which means that in the meantime, the sources that we have there, which is coal and other, will have to be substituted by other power sources. As far as the number of units is concerned, if we have 4 large units built in the Czech Republic, regardless of when, then the SMRs will be, the number of needed 300 SMRs will be at least 10. And this very fact gives us hope that the price will be bearable. I want to be economic enough, because we are talking about the fact that they are 2.5 times more expensive than large units. But we are talking about a situation when we are not really sure how much the SMRs will cost. Even with large units, the final price is much higher than the price given initially. So it's very difficult now to actually say how much we will pay for an SMR in 15 years, because it's an area that is rapidly growing and something I don't dare to tackle. Now, coming back to the graph that I showed when we had 4 large red blocks, red units in the and 10 green above, it was a very ambitious plan. And of course, we know we will need thousands of people. It can be 12,000, 7,000 people that we'll need, but the number will be really large. That's on one hand, but on the other hand, we desperately need these units. So there's no other choice. We have to find these human resources, or at least to do everything in our power not to have people fleeing the Czech Republic to Poland, for example, to work there in power sector. And that's it. Mr. Zdebor is standing up, which means that that's the end of this panel discussion. I will let him close it. Yes, thank you to all panelists, to my colleague, Mr. Marek, for his fantastic moderation. We had some more time to have a discussion, which was also great. So now let me close this first session, this first round table of the day, and I will give you as a token of our gratitude our in-house honey. All of you, please enjoy your refreshments and coffee break. And because we took some time from the break, we will also prolong by 5 minutes our coffee break. Thank you.
Mikrofon tady. Raz, dva, tři. Raz, dva, raz, dva, raz, dva. No ono tam něco je, ale vypadá to, že je to děsně slabý. Teď tam je ten zvuk. Raz, dva. Raz, dva, tři, čtyři, pět, 6, 7, 8, 9. Teď tam ten zvuk je? tak tam tohle, když tak okno nechte otevřený. No, ale teď tam ten zvuk je. Raz, dva, raz, dva, raz, dva, 3, 4, 5. Raz, dva, 3, 4, 5, 6, 7, 8, 9, 10, jo, to fakt ne. Nevím, no. Je to divný, no, tohle. Já ještě s vám zkusím ostatně.
No, slyšíte mě, jak to slyšíte? Je to dobrý? Už to lepší? Rozumíte tomu v pohodě? Dá se to?
Na uhlíku.
Jakým si jde?
Skončíme s uhlím.
Tady to někdo spolknul.
Ale si ho možná schraňuje, jo, on ho dal zde.
4, 5, 6, 7, 8, 9, 10, raz, 2, 3, 4, 5, 6, 7, raz, 2, raz, 2, raz, 2, 3, 4, 5, 6, 7, 8.
Naše velké firmy žádná nevyčarnáme, že on je přeběží. Já mám tam, když tak vypadne.
Ale to už je správný,
ono možná bych chtěl administrativně stanová. To by bylo asi dobrý, když si ráno s někým obyčej, jo, ale prostě co tam bylo, že někdy ty lidi dopředu, asi problém, ale jako teoreticky prostě je tam jako optimální podnikatelská vlastně. No tak se bohužel poradit, a je to čistě špatný. Takže to nemá do odpadní. Kombinace které má pečel, ale dali se tady tam tak pojilo. Přesně, ale to se to těch serverů a podobně. Právě metro, nebo přes moře, jo, tak moře nemáme, ale já to děláme právě. My řešíme do materiálna muziku, já se omlouvám, já mám tam své nedá se No, that's exactly.
Jo, mělo by jenom zkusit. Jo, musí být jenom tady, musí být povinná, on musí tady být zelený. Kdyby náhodou to někdo...
To někdo přidal.
A když tak počkej jenom to ošmatan, až připevnější zpátky. Tady nahoře je ukazovátky. Tohle to tlačí úplně vpravo.
To je ukazovátko, to prostřední.
To
je doprava, to je zpátky.
A ty spodní, ty spodní, ať nemačkají to nějak vypíná prezentaci a tak.
Jo, já si to budu zapnutí. Dobrý. Musím být. Znalej.
Jsme tím mě dali na nabíječku, co to dobijou. A vám tady jeden necháme a vybíráme.
No, vidíme. Jo, to je možné, že si totiž tahoval vrtec vina.
Tak tady máte červená. Tak tady to je druhé, jo? A my jsme asi na
Jo, ta prezentace se člověk nahrává.
Jasný, jo. Mě říká kolega, Jirko, máte právě. No, tak to má. Jak to bude prezentace ne, přijali naše pozvání a když se to velmi líbí.
No, nebo pan Dovel asi může nahrát chodit do města.
Jo. No, dobrá. Kolik to bude začínat? Jo. Oni asi ví, jak se působí. Jo, jo. Ne, tak jako když nepropadne, jako dobrý, jo. Když tak tady je druhý. Jo, druhý strany. Jo, jde o to, aby nedostali rák.
Raz, dva, tři, čtyři, pět. Teď tam.
Jo, perfekt, to dobrý. Takže už se stane. Asi to bylo lepší.
Raz, dva, tři.
Tak dobrý den, já bych vás chtěl přivítat na sekci číslo 3, která volně přechází z diskuze, která tady teďko probíhala na téma jaderné zdroje tepla a dálkové vytápění. Já bez dlouhých úvodů, protože vlastně plynule pokračujeme, tak bych rovnou požádal tady. Pardon? Není slyšet? Jak je to možné?
Okay, so let's start. Hopefully you can hear me. I don't want to prolong the introductions, so let us move to the topic of the nuclear heat generation for district heating, and the first to take the floor will be Ms. Kubikova from Dusan Škoda Power. The floor is yours. Welcome. I will talk about heat generation turbines for NPPs, and I will continue the topic that has been already introduced by my predecessors, by Mr. Procházka and others. I want to talk about the specifics of the turbines for NPPs, and I will talk about heat plants, about nozzles, about corrosion, etc. As you've heard before, in our portfolio, we have a large number of various applications for our steam turbines. For example, we use them for CCPP, for waste burning, incinerators, SMRs, NPPs, and we are also working on air turbines. As far as the NPP turbines are concerned, this is the output of 5 to 1500 megawatts. Low productivity are high rotation turbines, high speed turbines that can be used for micromodular and small modular reactors, and that can be applied in Dukovany or Temelín. As far as turbines for large NPPs and SMRs and micromodular reactors, main thing I want to point out is that we are well ready to satisfy the needs of third generation reactors. We can provide solutions for micro and small modular reactors. We cooperate with a number of companies such as NuScale, Nuart, Rolls-Royce. We're in partnership with them. We have a number of solutions for different fins, for different rotations, speed for blades. We want to keep our turbines very flexible, anything from 20% till full capacity. It all, of course, depends on how much we want to use renewables. We also streamline regeneration and streamline the high pressure of steam turbines. Here we see a design that are very schematic. It's a scheme or a diagram for an NPP, where we see the circuit for a turbine. You see a typical turbine for an incineration circuit. A steam turbine starts with the separator, then there is an expansion. If it's a one unit turbine, there are no overheating moments. The steam is already overheated and the expansion starts. It's important to realize that the output dryness or moisture or humidity at the end of low pressure unit is roughly 90%, which is very similar to in case of NPP turbines and for the burner house turbines.
But the parameters are roughly the same in terms of the pressure, but with much lower temperatures. We are talking about, of course, the big-sized nuclear plants. They have big throughputs and big volumes flowing through, which is obviously related to the size of the blades and the robustness of the whole machinery. The turbine for the combustion chamber, the incineration chamber, is about up to 100 megawatts, I would say. Of course, you can use also air cooling, but definitely not by definition for the nuclear power plant. To talk more about the heat supply installations, heat power plants, and the blades. Whenever you design a steam turbine, you need to take into consideration the optimized type of operation that this machine will spend most time in, 60 to 100 meters per second. Then there are two problematic phases or stages, which is the stuck and low conditions. You can actually operate it, but in the very non-economic conditions. When you have a big demand, then simply what happens is that you don't get almost any steam into the turbine, into the back, into the rear side of the turbine, and the temperature goes up. Now the blockage or clogging essentially is the other problem. Most of the opposite problem, I mean, most of the steam goes into the condenser, and the final stage blades can actually be overheated and overstrained. So axial speed and counter pressure and humidity, these are the main parameters. The sources of erosion can be either wet steam or cooling. Before the steam gets dried up and heated up, what the danger is erosion by wet steam. This is on the incoming flow. And if you can't increase the temperature further up, because you could destroy or damage the pipeline and all the related technology, you can spray using the water nozzle the equipment, which actually brings the temperature down, but unfortunately it has a downside to it. So the cooling by this method has a downside to it, because you can actually destroy the blades at the end stage. That is what is known as erosion map for each project, which is the graph that the ratio, the absolute erosion decay to the erosion limit of the blade based on the back pressure. So you specify the back pressure and humidity, and you create this sort of erosion map. And because you see all the types of operations in one and the same graph, you can actually optimize the protection levels and methods of protection of the blades. Once you've found out that yourself well placed for installation and you've already installed the turbine, we have a monitoring system. It's called Turbo Life Care System, and we monitor the life cycle of the turbine. We do experimental research on erosion on a long-term basis. As you can see on the right, in the right top corner, you see a picture, and you can see also the pictures down there. That's the erosion stand capture, sample capture system. So you start with a sample and you conduct erosion tests. And you test all sorts of coatings, all sorts of surface treatments. The graph in the middle of this page shows you the proportion between the erosion rate and the time of turbine operation. This violet curve shows the base material The remaining lines essentially represent the different coatings and surface treatments that we tested. You can also see the base phases of erosion, nucleation, creation of or development of erosion needles, and then stabilization. You can suppress erosion on both types of blades. This is a photograph on the right-hand side in the bottom page. It's a special type of coating. It's a Teflon-based surface treatment. We use PVD coating or stellite welding, and you can see the deposit system that we use, the piece of equipment that we use in order to provide the coating to the surface. You can also see during a visit to our experimentation center the water nozzles that we use for one of the things that I already mentioned, to cool down, if necessary, the blades, and this is by using the water spray. You measure the water spray nozzle position, the steam flow, and the radial, simply the stream flow. You can see the scheme down there at the bottom right corner, and you can see also what happens if we want to cool down the process. For those of you who can read well and see well, people told me they wouldn't be readable very much. You can see the pressure of the water there. It's 3 bars. This is where you still see the pressures, I mean the droplets of the water, while if it's 16 bar, which is on the right, the droplets are so small, so tiny that you can't really see them on the picture. Last but not least, I'd like to show you the Turbo Live Care system. This is our monitoring system, and its core, the brain there, if you can take that as a brain of that piece of picture, is the monitoring system that sends data from the power plants to our server. And this is in real time throughout the entire period of the turbine. Above that RMS, which is the brain of the system, is a module that measures the early warning system, for instance, defect monitoring, monthly reports that can be customized to customers' needs. The control room simply gets or can get exactly the kind of report you want to get, so that it reports the data that you want to capture. As regards erosion, we also do erosion monitoring, rubbing monitoring, timing, etc., etc. My very last slide is showing what kind of output you can expect from that monitoring. You can see the black line there, just the reduction of material, decay of material between several years, 20 through to 2023. And down there in the left bottom corner, you can see the real life screen, print screen essentially, of what the operator sees in the control room from a Doosan turbine. Thank you very much for your attention. All right, thank you for your presentation. Ladies and gentlemen, your time for questions. If there are no questions, I don't see any questions there, so I'll take the liberty of asking a question myself. I've been asked this question myself, but I couldn't answer it. New Dukovany unit, and what will be the turbine look like for new Dukovany? Will it be a half circle or full circle turbine. Thank you for that question. That is source of some concern for us. I am not the best person to ask, but in my opinion, we are considering a full circle solution. This half circle solution was also considered, but we are pretty much certain that we are prepared for a full circle turbine. But I believe this will be a full rotating solution. Any other question? I can't see any hands up, so thank you very much. And now I'd like to give the floor to Mr. Čermák as the second contributor to our conference.
You can hear me well. My name is Martin Čermák from Sokolovská Uhelná, which is a traditional name referring to our coal industry roots, because we excavate, extract and burn coal. Because we're under the transformation, then we changed the name partially to SUAS Group, which refers, on the other hand, to our coal-less future. I have two goals in my presentation. The first one is to show you that ČEZ is not the only company in the Czech Republic. The second goal is that we are very serious about SMRs. To begin with, let me tell you a few words about Sokolovská Uhelná. We are operating only one mining location in Jiří, when we have 3.7 million tons of lignite extracted annually. We operate 3 power sources. 2 of them are coal power plants, Břesova with 250 megawatts of installed capacity. Tisova, it's a power plant roughly of 380 megawatts installed capacity. We also have a steam gas cycle, 2 times 200 megawatts used as a peak source. As far as other activities are concerned, namely heat supplies, Sokolovská Uhelná supplies the region of Karlovy Vary with heat. Roughly 1/3 of households is heated thanks to our operations. This is just to give you a picture of what mining looks like, but I think you're perfectly aware of that. We want to be at the table when SMRs are discussed. For one reason only, we can never be sure when the market and the government will say that we cannot mine for lignite anymore. We do have enough deposits of lignite in our country, and we can go well beyond 2030 in our mining. 2040, sorry. But our government decided that we should stop processing lignite by 2033. There is also a recommendation document from the Coal Commission who refers to 2038 as the end year for coal. But I think this will be the case. I think we will have to even prolong the deadline and go beyond 2038. This is my personal opinion, however. Because what are the alternatives? Gas sources, but we all know what's the story with gas, how the prices are not, how the prices are very volatile. Renewables, another issue. We know that we have to find something that will be stable enough to substitute coals. And basically, this leaves us with nuclear power generation as the only substitute. And I used to work for 6 years at the Agency of Nuclear Research and Development, and we were working on something similar to an SMR. I don't want to bore you with our company history and operations, but just to show you the general picture, we have prepared a general transformation and transition strategy with 6 branches. Clean energy is the first one, when we want to build 200 megawatts of installed capacity on our locations. For the time being, we have the biggest battery storage site that we, power capture and storage facility that we will be extending. We want to use coal in chemistry because we have a lot of coal or lignite to explore and mine. So we're currently thinking how to make use of the areas that we have in our possession, which is roughly 85 square kilometers, which are mainly, which is farming land. So it seems that we are the biggest farmer in the country. Real estate is another pillar of the strategy. It refers to residential, industrial development. Residential development would be connected with our brownfields, which we will be trying to bring back to use so that people can live there. Technology, this is our machinery, equipment. We are trying to find new markets for these pieces of equipment because we are well aware that we will soon stop mining, so we won't have any use for them anymore. So there is a separate transformation program for these pieces of equipment. Service and sport and relax. These are other branches where we are trying to enter the market. Here you can see a few images of what we do. This is the study that we are trying to bring to life in an open pit mine that has been already flooded. It's the biggest such area in the Czech Republic, and we're planning some redevelopment activities in this location. But now let's move on to the main topic of today, namely SMRs. Sokolovská uhelná entered the negotiations and works of the SMR task force that was established in the Czech Republic under the Ministry of Industry and Commerce. As one of the participants, we became an open stakeholder, and we are interested in placing one of the SMRs in one of our locations. This is why we started cooperating with the Czech Geological Institute in preparing a geological survey in our locations pursuant to the for nuclear safety, so that we can exclude any criteria, or we can map any exclusion criteria that could prevent us from having an SMR in one of these locations. The locations are 2 in questions. One, it's in Sokolov, near to the coal power plant that we have now operational, or Vtasova area facility, where we have the steam gas cycle, and the Tisova power plant. They are both near Sokolov. We don't want to stick to only one for one simple reason, because in this region we have quite intense seismic activity, so we have to find out whether there are no exclusion criteria that would make it impossible for us to continue with this project. We have to be smart about it. We have to do some research and survey to be sure that at least one of the locations that we've selected is suitable for placing an SMR and will be in compliance with the decree I've mentioned. As far as technological limitations and the demand for a supply of heat in the region, we don't want to go for the smallest possible solution. We want to be somewhere in the middle, somewhere between 400, 500 megawatts of installed capacity. So it could be 2 or 3 units with a lower capacity, but these are roughly our ambitions here. Number one, because of our technological capacity and the demand in the region. And also, we have to factor in the capacities for supplying the source, for sourcing, and for the, we have to factor in also the specificities of the region. In the previous session, a colleague from CES showed you a schedule for their the investments, and we have a similar program, similar schedule, probably based on the same data set from the same source. We are planning for commissioning the SMR roughly in 2035. If somebody says that we are over-ambitious, I agree. This is a critical path. I think this is the earliest possible time where we can commission the SMR. So we have to think what we can do until then, how we will supply heat, whether our coal sources will be in operation until then, and how much we'll pay for it. To keep these sources operational until we commission this larger nuclear source or the new nuclear power source.
This is a preliminary roadmap, shall we say. This is what we are planning. If the Czech Geological Survey Service gives us the green light for that. So by the end of this year, we should have this final statement from the Czech Geological Survey Service, whether any of the 2 locations would be reasonably suitable on a preliminary basis for a nuclear power installation. If that is the case, we'll start to work towards a more detailed roadmap, and will of course involve we'll spend several years working on a very detailed geological survey. And the last bit here to prove that we are really serious about our developments here, we've joined the US Department of State's program called Phoenix. And there were 14 countries involved with about 30 companies taking part, and they asked for money for feasibility or pre-feasibility studies for small nuclear installations. We were one of the 3 successful companies, one of the 3 successful bidders. Slovenské elektrárny, the Slovak power plants, and the PKN Orlen for Poland were the 2 other companies that were successful in bidding. So this is my way of proving that we are serious about it. Thank you very much. Thank you very much. Questions? I'd like to ask a question concerning that selection process. Are you ready to go ahead if it looks promising in terms of further development for the individual projects, talking about the SMRs? So will you be the operator as well, including staffing? Thank you for this question. That's a good question. We've been racking our brains with this for a long time, probably a bit preliminary or way preliminary. It's way too early to ask, but we will be discussing the models of operating it. There may be several models in operation. It may also mean that we would actually be working together with chairs, because we are ready to sign a memorandum on knowledge sharing with chairs. We want to be, we will not be the first to hit the mark, so to speak. It'll be chairs in the Czech Republic, but we might be the second one, or maybe this could be something that would be jointly operated by chairs and ourselves. And I take the liberty of extending this question. So you are ready, as you've just said. Are your neighbors ready too? Because if you look at the map, it is a nuclear installation. And towards the west of you, just across the border, is Germany. And one can expect some statements against any new nuclear source. Of course, time will tell, but we are on the territory of the Czech Republic. We have our experience with Temelín, and we know the story there. Whether something similar can be expected from Germany, that's a big question. I might actually answer this question by saying Germany is in fact considering contracts with other countries who would supply power from nuclear reactors. Thank you. My question is, let me put it this way. I'm very happy to see that there's this cooperation with chairs in the pipeline. So I suppose you would be using the same type of the small modular reactor, which I believe would be very suitable for the Czech Republic. Have you talked with chairs about the possibility of you taking part in the negotiations with the suppliers, together with chairs? You know, this goes back to what I said earlier on. That's really the biggest task here, the most difficult task, to pick the right design of the small modular reactor. That'll be the best suited design. And not every single design is suitable, definitely not the Russian one. And there are certain models that I do see as almost ideal. Okay, understand. Let me just repeat what I said at the beginning. We are at the beginning of the process. You know, we've just started the journey. However, Dr. Zawodsky and myself shook hands on it. We really want to go together, and our lawyers are working on a memorandum of knowledge sharing. And we would like to take part in the selection process as well. If chairs decides to go for a particular design, it would be very reasonable to replicate it on other parts of the territory of our country. And the second part of your question, can you just remind me? You've answered that the discussion. Yes, so is the assumption that we would take part in the discussions with our suppliers, and we want to be part of that process. We're in touch with some of the manufacturers. Rolls-Royce have visited us twice, Holtec, Hoscale, and others are coming and knocking on our door, because the ministry, the Department of State of the US published the results of the 3 winners of that bidding process. Okay, thank you and good luck. Thank you very much. Now, ladies and gentlemen, I'd like to ask Mr. Šroubek to give his presentation. Good afternoon. Thanks for inviting me to Brno. I mean, sorry, from Brno to Pilsen, I should say, actually. Our project has been mentioned here several times during the morning session. It's fairly generally known. I would say it's only a few years younger than myself, so everybody's heard about it. In Brno, as has been mentioned, almost everything is based on natural gas. On top of that, we have the waste incineration plant, and we are currently preparing it for another installation of a new boiler. We've installed 400 megawatts thermal. We supply over 100,000 households, and the whole network covers over 300 kilometers of piping. We've started the preparations for delivery of heat from Dukovany, and we started by changing the pipelines from steam to hot water. But there used to be a need for hot steam being supplied for various companies like textile companies, etc., etc. But the industries have evaporated, so the need is no longer there, and we started to prepare for the heat coming from the Dukovany installation. By 2027, the whole network should be ready for hot water piping, or should be already installed. So we'll be ready for Dukovany. Apart from that, we are also extending our network, and we combine this with installations. New development projects are supplied from our network, and if there are any gas boilers locally providing heat, we try to connect them and try to convert them to our CZTE, which is the acronym covering the name. It's over 300 gigajoule in building, and other projects are also in the pipeline, so to speak, that are going to be selected and delivered. About 20% is delivered of the heat is delivered by the waste incineration plant. 80% is provided by combusting natural gas. We also have a project of heat generation from biomass, and there'll be about 15% of heat delivering from biomass, meaning pellets. And in parallel with that, if we extend the waste incineration plant, almost half of that heat will be delivered by a low emission way.
Post 2030, once the units in Dukovany are commissioned, we will take 60% from Dukovany, 5% remaining. We will have to use gas, natural gas for peak situations, and probably we'll have to, if it happens and the law allows, we will be highly operational, highly effective. We are not the first or the last who will be building new pipelines and new this installation, so this is not something to be afraid of. It's been done before. What are the advantages of using the heat from nuclear power is obvious. You know all this. Using heat from the Dukovany units has been already regulated in many documents prepared by the governments, by self-government in regional and central bodies, so they enjoy large support. As far as technical parameters are concerned, we will supply 2 million gigajoules heat thermal per year. The capacity will be 200 megawatts, and we will be able to be zero emission to cover even the peak. The investment will be at roughly 20 billion crowns, and it's not a lot, but this is only part of the investment. The other part will be covered by ČEZ and their funding. They will prepare the installation on the NPP, facility. We've had that, and they will be the one responsible for preparing turbines. We will have to also have connection installation built, which will cost roughly 45 billion crowns. And then there will be some developments in Brno, the city, hot water pipelines, steam pipelines. Some of it is at the design level, so we have to now be open about it, that 1/3 of the budget has been already used for the design and documentation stage. When we were discussing this project in the past, we were already mapping the tunnels that could be used because they were in a fit condition and they don't require any extra works. The path or the route has been already confirmed in the land use maps, so we should not have any issues with regards to getting and obtaining construction permits. Based on the expertise from the Temelín projects, we would like to get permits where there are already pipelines, pumping stations, and other infrastructures such as bridges. While preparing the land and property for the investment, we have to remember that there are the land is very narrow, and it is very difficult to work on such narrow lands. We want to not really buy out the land. We want to, I think we'll go with a scenario of easements rather. These are some technical parameters for the hot water pipeline. The routes, there are four pumping stations on the pipeline. In peak times, in winter, probably not all of them will be necessary. The hydraulic calculations are underway. So once we're ready with that, we will know what kind of parameters will be required from these pumping stations. It will be probably annually less than 600 gigajoules per year. In the city itself, we will continue the route and the path that has already been built. It is the northern hoof, as we call it, and we will connect two different installations here because this was something that was already designed for and factored in the past. Of course, we have to respect and follow the requirements for the contractual cooperation with ČEZ, who is our main heat provider. We have already signed memorandums and we have preliminary contracts for heat, and in all our works we will have to comply with all the contractual provisions so that we can smoothly develop the project. We have already received the AR decision, and it has been said that we will not have to make this big assessment, EIA, of the environmental impact. So now we can continue with other documentation for getting construction permits. In 2029, we will open the tender process for the supplier, and hopefully we will be managed to close the construction until 2030, and we can commission the final supply then. This will mean lower emissions for Brno. We will have a very stable supply source of heat, and we will have a supplier who is a long-term partner for heat supplies. Thank you. Are there any questions, please? There is one.
Děkuji. Já bych se chtěl zeptat, jestli plánujete připojit i ty vesnice po cestě.
Will you also connect the villages that are on the way of these installations of this pipeline? Definitely. We contacted all the self-government bodies. They are interested, and at least we will connect at least 3 installations, Krumlov, Livančice, and 1 more. Everything else is under discussion, whether we will actually connect these installations. We are talking about small schools, maternity schools, and maybe offices, so there's not a lot of consumers that would be interested in our supplies. Other questions? You did not talk about the technical part of the Dukovany project. How will you use the turbines in Dukovany? Will you use all of them or half of them? I think this is the question you need to ask to chess people. I don't want to talk about it really. Every single unit will be supplying the heat, or will be able to supply the heat. So when there is a downtime, we can use a different unit for the supply. I don't see any other hands raised, so thank you for this part of the session. Now, Mr. Bartak. Hello, my name is Jan Bartak. I'm the partner and the president of the French consulting company Nuclear Advisor. And this is my debut because it's the first time that I'll be speaking outside France about a very small reactor that we are developing. It's a reactor for generating heat. Galogena, it's in French. I think it sounds a little bit political because Žena in Czech, it's a woman. And of course, one might say it's yet another project. Why do we need that? So let me shortly brief you why we came up with it. In Europe, there is a massive drive towards moving to heat networks, heat installations. They should build up 1,000-fold in the future. And of course, this will be under 110 degrees centigrade or under 90 degrees centigrade. So there is a drive for that, and Europe wants to have these pipelines decarbonized. Decarbonization is not really very simple, and I think you all are well aware of that, probably better than I do. But if you have a look at France, today, roughly 60% of the pipelines have been decarbonized, or the grid has been decarbonized, depending on... In France, we use geothermal energy in the vicinity of Paris, and biomass is another source, popular source. When you look at the latest EU directives, we know that biomass is not a long-term solution. There is not enough of it. There will be a lot of competition here, and the production of biomass will be decreasing and will be used for other purposes than incineration. So, yes, we do know that there are other sources, nuclear sources, that will allow us to decarbonize heating installations.
The other aspect is that there is a program in France called France 2030 that was announced about 2 years ago by President Macron. And in this program, 1 billion euros has been earmarked for new innovative projects of nuclear reactors. And there is a competition announced, particularly for early design studies, the pre-concept, Pre-technical design, simply concept-based competition was announced, and I can tell you that out of 1 billion euros, 500 million goes to that project that is already well advanced, and the remaining 500 million euros will be dispersed between, let's see how many there will be, usually startups. I think there's about 15 various startups, all sorts of projects of fast reactors, molten salts, that kind of thing. And these are grants. These are not loans, you need to understand, by the government, but the government is going to subsidize through grants only 1/2 as a maximum. The other half needs to come from private sources, from private investors or other companies. Nuke Advisor is consultancy, so we were thinking, how could we get involved? We've been able to provide consultancy services, doing design reviews and that kind of thing, due diligence and that kind of thing, to many of those projects. Then we thought, well, why not we go ahead and design and develop our own reactor? So we started working on it. It took about a year developing the initial concept, and we were looking for investors. We talked to many investment funds, and we were trying to raise the venture capital. And then a medium-sized industrial company called Gaucher, Raphael Gaucher being the president and owner on the top left corner of this page, he essentially was looking for other options to develop his company in the nuclear sector. And his mission is to prove that a small, agile company can actually develop nuclear reactor perhaps faster than EDF, that has all the competence and all the skills, but it's a big mammoth. It's a huge beast that takes time to decide. So 12 partners from Nuke Advisor and Mr. Gaucher. And Mr. Gaucher is ready to put the money into the first half of the project, and we bring the intellectual property of what has been developed. Now, in France, it's important that the project is accepted in the nuclear power energy ecosystem, the sector being very strong in France. If there's no support by key industry players like Framatome, EDF, Orano, and other institutions, the ministries and other institutions, but also the operators of the heat supply networks, Dalkia, NG, EDEX, if it hadn't been for their approval, we wouldn't go for it. We visit all of them, and to our surprise, we were accepted in a very friendly way. All the people realized that decarbonization is not an easy task and that we need to find various ways to achieve it. So, having considered the context, I can now tell you more about the reactor. Kalajina, it's a reactor for heating solely. It doesn't produce electricity. This is essentially covering what I've already said. We also talked about this with municipalities that also operate heat supply networks, just to test the ground and see if they will be in favor of this kind of development. So we really paved the way towards success. Now the technical side of things, it's a 30 megawatt thermal reactor power reactor, and it's a training type of tank design derived from the pool type research reactor. And our thinking behind this was that this is something that has been well established and spread across the world. Although 30 or 40 kilometers distance would not be a problem, but we thought it'd be good to use something that is based on this design. Our approach was based on finding innovation, not perhaps in the very design of the reactor, using, for instance, molten salts, but rather using whatever is well established, the state-of-the-art knowledge and technical inspiration, and the application is the innovative aspect of it. So we thought the reactor should be as safe and simple as possible. The inherent safety that is derived from the physical properties of the system, with passive systems and the smallest number of systems as possible. And it is based on the assumption that the regulator and the supervisory bodies will actually allow us to build this near big cities. I don't need to explain this for too long, I think. This is the type of linking up, or how this would be connected to the network. Whether or not you use multiple sources, there will be a gradual replacement of the traditional sources. And just like you have certain priorities in accessing the grid, when you generate electricity, this low emission or zero emission source would actually have a priority in accessing the grid or the network. So the operation time would probably be longer than the fossil-based sources, which would be essentially used for peaks. Of course, we need to eliminate by design the core melt. That was one of the key aims of our design. And as I said, it's a pool type of research reactor. Essentially, the core is in the pool. If the worst scenario happened, then you have natural cooling by water for dozens of days. And the reactor vessel would have a natural circulation, so no pump. You saw the temperatures a maximum of 110 degrees Celsius, which means that it will be around 5 bar maximum pressure. That rids you many problems that high pressure systems, phase shift, and that kind of thing inherently brings. This is what the reactor looks like. Again, we wanted to make a very simple project, robust, with low pressure, but natural circulation. Can I use the pointer? It works now, thanks. Sorry, it doesn't. Anyway, the active zone is that little red area down there at the bottom as the core, about 1 cubic meter. The vessel is about 15 meters tall, and there's a riser or column in the center, which will actually allow the hot water to go up, and the rest of the vessel is essentially occupied by the traditional piped heat exchanger. This is where the primary water goes back, and this is the intermediate circuit. Water will go through the intermediate circuit, and then heat transfers to the network, and the pressure conditions are such to make sure that the primary circuit is in lower pressure than the rest of the zones.
It's a 30 megawatts design. We want to have 2 modules or 2-unit module in one installation. But if the network is bigger, then we can include more of them. The used area is relatively small. The goal is again to simplify the whole system to use the fuel which is not extremely enriched. As far as the fuel is concerned, we are thinking about the plate fuel used for research reactors, because there's a number of advantages of that, or a classic water reactor rod type of fuel. And again, there are certain advantages, for example, when it comes to availability and the production capacity. The decision has not been made yet. We are thinking more towards the plate type fuel, but the decision will be made towards the end of the design process. Preliminary calculations and estimates that we have made rather indicated that we should opt for the plate fuel. And now the schedule of works, you can see what we are aiming at. In the 2030 France program that I mentioned, there are 3 stages planned. I'm not sure whether it's the proper way to say it, but it's a conceptual design stage, when we have to submit to the nuclear authority safety options file. So it's not a PSAR, but rather a preliminary document where we indicate certain characteristics to the authority, which in turn has to approve or dismiss the document based on safety and safeguards and securities. So we have 2 iterations. We provide a preliminary documentation to the authority, and at the end of 2025, we prepare the final safety options file. Then we would proceed to prepare and submit the basic design. It would take roughly 3 years. At the end of this decade, roughly 2029, 2030, we would move on to the detailed project, and we would start construction. In France, the crucial element is, in terms of regulatory requirements, is here. It's not really a construction permit. It's rather a document that you need to obtain based on the evaluation of your safety report, PSAR, from the regulatory authority that actually gives you a green light to begin the construction. You have to submit your request at least 2 or 3 years in advance. So even though we would be glad to speed the things up, but it feels like this is the only realistic schedule we can hope for. We didn't want to be optimistic about our activities, because when we look at currently developed projects, we believe that the optimism is abandoned. But these projects are extremely complex and sophisticated. And we should have the first client roughly around 2025, 26, and it's crucial to have one. Otherwise, we won't be able to get funding to finish the project, which will cost dozens of millions of euros. We established a company. We named it Kaložena. And now we are recruiting engineers. We already have the general technical officer working. Maybe next year I'll give you some more details about these projects, but that's it for now. Thank you. One more thing. When we make economic estimates, we look at the entire Europe, but the first client has to come from France. So this is very important for us to find the first client in France, because we are building it in France according to French laws and regulations. And just to add to what has been discussed here today regarding the business model. So we have established a company who will have two branches. One will be building the reactors on a turnkey basis, and the other one will be the operator. So one of the branches will get licensed for the investor who wants to build and have the reactor, and the other company would operate the ready reactor. This is a typical American model. There are some cases for research reactors that operate on this basis, but we truly believe that even though this is not something very common nowadays, I think in future, we believe that in future it is viable. And in France, the only person who can request to be licensed is the future operator of the installation. So there is no other option. Are there any questions, please? Thank you for this interesting intervention. To understand you well, the Kalužina company will be also the producer, the manufacturer. How? Yes, it will be responsible for manufacturing, for generation. We won't be doing everything. I think we will have to cooperate with certain subcontractors. We will get control rods probably from a different manufacturer. Maybe it will be Škoda Jaderní. Yeah, JS could be our supplier. And the other company will be the operator. Yes. Thank you. You said it was 1 cubic meter of fuel. Do you have any idea what you'll do with SNF? Well, you will store it. Do you have a repository? That's one question. The second question, what is the feedback you get from the French society regarding the new nuclear sources? The first technical question, the second a sociological question. So, starting with the technical one. If we opt for the standard fuel option used for water pressure reactors, that's not an issue, because we already have in place the recycling cycle for the spent fuel and used for the MOX fuel production. So what would happen is that we would just enter the existing cycle of recycling. In case of the other type of fuel, the plate fuel, then we have very common type of fuel used in research reactors. Such fuel can be processed technologically. It's not a problem. In Australia, there is an Opal research reactor, relatively new one, and the spent nuclear fuel is processed by Orano for the Australians. So we do have the technology to process it. This spent fuel, we have already talked to Orano. Probably it would be more viable economically if we used the rod fuel, control rods, but because the process is closer to home, but the plates are have other advantages because you have aluminum there and it melts earlier than steel, sooner than steel. So in case of a failure, there is not an option to melt the corium. The other question, when I saw the data saying that 70% of Czechs actually support nuclear energy, I was really astonished because in France, I don't think it's such a high number. We are in discussions with various municipalities, and obviously we go for the mayors who are recruiting from or coming from the political parties that are more inclined toward the nuclear energy. But it's difficult to answer your question. I think if you use proper arguments, if you show the results of research reactor operation, I think there shouldn't be any resistance towards it. I remember in Grenoble, I don't know if you know, but there were roughly 10 reactors, research reactors there, operational. They were being decommissioned gradually. There was one reactor with neutron flows who was actually in the city, in the municipality. So I don't feel that there is a huge social pressure towards decommissioning or against the nuclear power. But truth be told, it's not only our problem. We have to face decarbonization. And if the government and all the authorities are in for it, then it's easier to actually persuade the society that these are the steps that are strongly required. Yes, if the government is very strong about decarbonization of heat networks, and one of the ways to do that is nuclear power, then there is actually no other option. Thank you. If I understood correctly, the prototype will be located based on where you find your first clients. My question is as follows. Wouldn't it be easier to get a client from the industry, so somebody who's looking for a small heating plant, because then you wouldn't have any issues with the public opinion? Have you tried to approach any industrial clients, potential industrial clients? And the other question, do you have any idea about how many reactors you need to be in black numbers, so to have it economically viable? I really liked your presentation because I can see that you will use all the fuels that are already existing. But on the other hand, it is something that is a turnkey solution adapted to the needs of the industry and of the demand. How many reactors do you need so that economically it makes sense? We will have detailed economic analysis in the following stages, but of course we do have a business plan in place based on what is being planned for in Europe, what is subject to decarbonization in Europe. And we looked at the 15% of the French market and 10% of European market, excluding Germany. So these are countries that are anti-NPPs, and the estimates showed that we would have to have at least 12 modules a year, and we included in our plan only half of it, and it still makes economical sense. Final question. If I understood correctly, because I did not read clearly your slides, you said that you will use control rods. Yes, only rods will be used for controls. Yes. And we already have 4 patents for this solution. but these are for the passive part of the system of the installation, or at least we applied for full patents, so it takes some time. Thank you.
Now, two more speakers, Mrs. Židová and Mrs. Šmurda. So, who comes first? Good afternoon. I'm Lucia Židová and I'm from Chemoprojekt, the general contractor for the heat supply pipeline from Temelín to České Budějovice. That installation has been mentioned several times today. I'll give you some more information about it. It works, so we can start. Can you hear me okay? Do I need to speak up? Currently, we are completing the project, the installation of the project. The investor is ČEZ, and ČEZ will be also the operator of this facility and owner, straight to the handover point in České Budějovice, which I understand is a slightly different constellation that is planned for Dukovany and Brno. Over there, it's ČEZ providing the heat, and straight from the premises of the heat supply facility, the Teplárna Brno will be the operator and owner of the facility. Now, this is purely ČEZ's installation. ELT will be an association of company, and Energie Stavební and Abaňská will be the two companies that will be the general contractors. The general designer, Chemoprojekt AS, in cooperation with KCH Projekt Pilsen. And I want to mention that the chief designer of the project, Mr. Šimurda, is actually not present. He's the co-author of this, but not present, but he's rightly mentioned here. And Mr. Broš, the representative of the CH Project Pilsen company, is here with us, who's ready to take your questions, and Mrs. Bielková, who is the leader of the team for documentation of the commissioning process and the main designer for the documentation. So she has a lot to say about the project, if you're interested. There's a whole lot of suppliers. You know the names of the companies that Motor, Tenza, and all the rest of it. Many other companies that have been involved in the project, they're sub-suppliers. You might think this is just a set of two pipes and some piping and a few heat pumps. So what's the big deal about it, you might be asking? True to say, in a way, but a project like this has gone through difficult situations, gets into a tight spot. Sometimes, as you know, whenever something bad happens and you're in a tight spot, the media gets interested, and that's exactly what's usually happening. We signed the contract between ČEZ and the subcontractors before Christmas 2021, so in reality we started off in 2022. The handover period is essentially now. That's the September of 2023. Next week we are doing the measurement A, the warranty measurement A, and subsequently we'll hand over the works to ČEZ. The warranty measurement B will then take place subsequently during the winter season, full performance. The location is pretty clear. Temelín through Hluboká nad Vltavou to České Budějovice. I think the history is well known. Tenza, the company involved in the design, started off building the heat supply pipeline, but they were not able to complete it. Although they've had some experience, they were not able to complete the project. And unfortunately, Tenza, having been unable to complete this, they had to quit. They started off with the production, with the installation, then had to cease, although they had all the things necessary for it. As you can see, this proves that it's not as trivial as it may appear. Then ČEZ decided in the end that they would run a new tender for the completion of this project, and in 2021, the general contractor for the completion of the project was selected. So as the general contractor, we started off by checking the design and as-built documentation. We had to amend it, adjust it, and one could see sometimes that probably at a stage when Tenza was already in some problems, so we had to make sure and double check that everything is all right. I don't think I need to dwell on the purpose of this work. So the purpose of it obviously is to supply heat to České Budějovice, the city. The performance is 8 to 100 megawatts. The annual supply of heat is roughly 750 terajoule. That should be enough to cover about 1/3 of heat consumption in České Budějovice. So it's a significant contribution to the decarbonization effort of the heat supply company, and there should be 80,000 tons of CO2 roughly annually saved. The temperature gradient is 140 to 70, and in the summer 90 to 70 degrees Celsius. The pipeline, being 26 kilometers long, is the third largest of its kind in Czech Republic. The longest being Mělník, then Opatovice-Chrudim. But we will only be number 3 in the Czech Republic until the Brno-Dukovany becomes probably the largest and longest pipeline for supplying heat to cities. And this is not anything new in that area, because Týn nad Vltavou, a small city of České Budějovice, is supplied in exactly the same way. Technically speaking, it's just 2 sets of piping and a set of heat pumps. If you look at the nuclear power plant side of things, you start with the heat output mechanical room with pumps installed, 26 kilometers of piping to České Budějovice and back. The diameter is 500 millimeters, DN 500, and the gradient is 120 meters. And there are 4 bridges, 5 bridges. Going in the opposite direction, going still from Temelín to České Budějovice, there is a pump-over station at Obora with 3 circulation pumps, and the central heat exchange station CPS2 in České Budějovice features 2 sets of 3 circulation pumps each and 2 mixing pumps. So we supply hot water to České Budějovice, Týn, and the cooling site, and we provide the regulation of water temperature based on the output. ČEZ will be the customer, but České Budějovice Heat Supply Company will be the actual company that will lay down the technical parameters. So 26 kilometers of piping, there are 4 pipe bridges, as you can see. Some of them are, I would say, nice in their architectural treatment, given that this is something just for industrial purposes. That's something that Tenza started off, and the construction companies had sometimes pretty difficult time to calculate these, to design these, and then realize them and implement them in practice. So it's in Temelín, then Hluboká nad Vltavou 1 and 2, and one at a place called Křivonoska. We also had to cover shafts and pits for crossing roads, and this is also for de-aeration, and there's a total of 32 shafts. And there's also an alarm system to indicate leaks. The Obora pump over station that is located several kilometers away from České Budějovice essentially sees the water just coming through the piping, and the cold water is pushed against the terrain because Temelín is at a higher altitude than České Budějovice. Then the circulation pumps and the mixing pumps are located at the pump station, and this is how you transfer heat from the network to České Budějovice. And essentially what the pumps do is that they compensate for the loss of heat in the heat exchangers, and the cold water is then pumped towards Obora, then to Temelín. The mixing the mixing pumps provide for regulating the temperature of the water going into the distribution water network, and there are obviously meters and some also measurement of the chemical composition of the water. This is just to give you an overview, and this is the end, the final slide of my presentation. Just a block diagram, not really very legible, but just in closing, I'd like to let you know that there is an association of companies, a group of companies that have gone through this project, and they have their hands-on experience still in their vivid memory of this. And I believe that this puts them well placed, makes them well placed for delivering something similar in the Dukovany to Brno heat supply piping. I know they've gone through, they have the field experience, and they know the risks, and I think it's best if somebody who's done exactly the same job just a few days ago, weeks ago, knows it. This is a completely different story than if you have a company that has the history of doing that kind of stuff, but the people have left the company in the meantime because it's been years. So this was something that we can hopefully offer to other investors, and hopefully they could benefit from it and replicate this experience. Thank you for your attention. All right, thank you for your presentation. Any questions? Good afternoon. My name is Vecka. I'm from the Heat Association company, Heat Association in the industry. Where do you go to get the water from? Is it from Temelín? This is the water from Temelín. Is there any issue that surrounds this? How about the refilling? Because as far as I know, the capacity of water replenishment of the feeding water is still running out. So was there any issue? Well, what happens here is that you fill up the feeder, and that's the end of it. This is different. It's not, what you're asking is essentially the loss of water that you need to replenish because you lose it in the cooling water. That's not the case. We already have the water, and my colleague would be better placed to answer that question. If you sometimes have to replenish a little bit of water because of treatment losses, these will be just minor volumes. I'm just thinking, is the connection, I mean, is it separated? No, it's not separated. It's not two separate circuits with a heat exchanger between them. I'm thinking they could also supply the water if any problem leaks, whatever, they could supply water from České Budějovice. If there were a leak in České Budějovice, we would also know about it in the feeder line. Obviously, first you need to get rid of that leak and then replenish water. Okay, thanks.
So I understand, well, it's CEO Král is not going to have an intervention because I do have questions for him. I don't know because he had an independent intervention. He's not here, so I wanted to combine my question or ask a question to the presentation by you and Mr. Schrobeck. Your presentation was extremely informative and expert, technical. And Mr. Schrobeck said that if we have the pipeline up and running, then we will have a fixed price of heating for České Budějovice. And we've just heard that it's a very technically complex solution that you just presented. And I do live in České Budějovice in my district, and I can see that there is going to be decommissioning of coal power plants. So how will this affect pricing of heat for us? Mathematically speaking, I would say it will be cheaper, but I don't think as a general designer we can in any way affect the pricing. But the energy prices are not calculated when you have the margin or the yield plus the production cost. You know what happened last year in terms of power generation. Mathematics is not enough to define what kind of pricing will be implemented, but I don't think it will be cheap. I'm afraid. No other questions? Thank you. And now it's time for Mr. Neumann to take the floor. Ladies and gentlemen, let me follow up in the footsteps of what has been presented by Mr. Schrobeck, and I will also try to answer the question of Mr. Král. I was asked by Mr. Zdebor to step in for the CEO because he is just too busy and he was not able to come here. I was not aware that he will be substituted by Engineer Židová in her presentation of the feeder pipeline. So I concentrated on how we can cooperate between NPP and the heating networks. Based on my experience, I know that the group of experts on nuclear power and on heating installations, these are two separate groups of experts, so I think it's a very good opportunity for us here during this conference to find a common language. And now, when we are talking about the heat pipes and thinking about the nuclear power source or other sources for heating purposes, it's irrelevant. I wanted to show you the longest heat pipe, Mělník-Prague. Based on what you can see on my slide, if we manage to build the extra unit in Dukovany based on the lifespan of the project, these reactors are here to stay for the whole century. So it's some food for thought. As far as the heat pipes from Mělník to Prague, they're really long. It's roughly 34 kilometers. Mělník-Třebořadice in this part. But because it's not separated, then also the next 30 kilometers of core heat pipes to Modřany district. So altogether, we are talking about 64 kilometers of heat pipes. And if we take the furthest outlet, then it's almost 74 kilometers long. We provide through these pipes as the capacity 650 up to 700 megawatt tons annually, which amounts to an average 9,000 terajoules. This network includes the Mělník power plant, Energotrans owned by ČEZ, and on the second end here in Prague, it's Veolia-owned network of 600 kilometers pipes in Prague. So it's the longest feeder heat pipe and the longest network we have in the Czech Republic. Here you can see the heat pipes going through first-class road. It's an overlay, overbridge. In most parts, these pipes are overground. This option has a number of advantages, and it will be a model used for that. The article that will be published in the All for Power, where we prepared the article together with the CTO of Mělník and with the head of Třebořadice plant, and I recommend this article. I'm the last before the break, and my bad luck continues because many of the projects have been already covered by my colleagues. I said there was 1,000 terajoules in the network. My colleague, Mr. Vecka, said it was 800, but it's irrelevant, I guess. In České Budějovice, there has been a strategy for a green city adopted, which factors in the situation of the strategy, or rather regulates the strategy until 2024. The strategy suggests that there is no place for SMRs without a heat network. As far as the feeder pipeline is concerned, and what Mr. Schrobeck already said, we have two possible options: to use exchanger stations or to use the central system. This is how we can ensure uptake of heat from Temelín. The current exchanger stations have a smaller capacity than originally. And of course, economically, it's better if we have these installations are close as possible to the design projected capacity. In 2020, we had them running at the full capacity, but they are really old and they had to be refurbished. This is the original state where the original exchanger station had only one branch, and you can see some calculations. This is the after the remodeling option, when you see there are two branches already with 90 megawatts each. Here you can see the monitor of a unit exchanger station with 6 main heat exchangers. This is the one that was two branch, and that was just another image. This is all in Temelín facility. You can see the exchanger stations with and pointed with an arrow, and the other installation is used for heating Temelín, and it's outside this diagram. So first we were talking about a 41-kilometer pipeline going from Dukovany to Bosonohy. There was a heat pipe installation in this municipality that was actually connected to it. Altogether, it's roughly 60 kilometers long. Here you can see in the table certain parameters that are crucial for this most significant pipelines in the Czech Republic and abroad. For example, Bohunice, Trnava, Hlohovec in Slovakia. Also, for example, the supply of heat. Here you can see it's 2,100 terajoules. And when you compare it to Mělník Praha, it's 9,000. As you can see, this is a mammoth type of pipeline.
And České Budějovice, we already said that, 1,800, 750. And Brno should be 2,000 terajoule. That's based on the presentation delivered by Director Šroubek that he delivered during the previous conference, heat supply industry days. I can also, I won't read whatever else you can read from this chart. You see the temperatures and the volumes and everything. That's Brno 1,500 and 3,900 for Ceboradice. I think there's a limit at around 9,000 tons. But why am I making this comparison? I did say that it doesn't really matter whether it is a coal, nuclear or heat source, but the piping is still the same, and the pumping station. I believe that that sets an example, a sample really, or perhaps a model to be followed for the Brno heat pipe. I realize that it's a technical detail, but something very important, and I do apologize for stealing this from you, from your presentation, essentially. I only took the liberty of marking out the places and lines on the map. So this is all about sharing experience, really, and putting to good use the knowledge and skills acquired. So both Mr. Král and Mr. Šroubek talked about this already during their presentations, and also the technical director Hora from Mělník and Mr. Liška from Třeboradice have also prepared their work on this. Talking about the SMR, I don't think I have time to dwell on this for too long, but I just wanted to point out that there is a public opinion poll that was done by the Public Opinion Poll Institute in the Czech Republic. And it sounds like that 50% of public would be okay with the idea of having a nuclear power installation somewhere near their location if it's at a distance that is longer than 50 kilometers, so not in my backyard. And also, there's a good deal of support in the general public if there are also private companies involved, because the main mission of the heat supply industry would otherwise not be met. I was shocked to hear today, I hadn't known really, that heat supply for SMR is actually not that much of a priority. So SMRs will be primarily used for electricity generation. That essentially means chopping up the big units into smaller units. That's the end of it, but not really making any contribution towards the heat supply. I've taken the liberty of putting these circular diagrams and the distances, the radii, if you like, the radiuses of the installations, potential installations, and the potential distances to be served and the areas covered. I want to say that the central and northern part of the Czech Republic doesn't seem to be covered. Czech doesn't seem to be covered. Czech doesn't seem to be covering this part of the Czech Republic with the heat supply projects. Now, back to the public opinion poll, the outcomes of it mean that unless things change, so all other things being equal, I am very sure that the people who do public opinion polls know how to manipulate people and know how to ask the questions so that they get the right answer. But all other things being equal, we can, at least for the time being, take it for granted that small modular reactors are acceptable to the general public as long as they are at least 50 kilometers away from their place where the people live. So the rest of it will be covered by heat piping. Kalogena being introduced on the program, on the agenda of our conference, I just wanted to say that they can't really do that job because no SMR supplier really deals with the issue of how to absorb heat from the SMR. Usually they just don't care about this because they don't know if they need to be regulating the thermal output, will it be the thermal output of the unit or the electric output of the unit. So it's completely in the haze. And one can hardly put his or her finger on what exactly will be the case. This was an exception. Sokolovská nedouhelná. I happened to visit that company about a month ago, and they said, SMR, no, not our choice. We have other plans in mind. In closing, I just wanted to share with you a statement by Josef Perlík, the head of the Alliance of Czech, the energy sector. He says SMR might actually find a way, but probably the way needs to be paved by the government or somebody else. So for the time being, this technology is not ripe. Thank you.
Takže děkujeme ještě jednou. Dotaz nějaký?
Questions?
Tak, jeden dotaz, prosím.
Yes, one question. I'd like to talk about diversity in the terajoule of energy supplied from Temelín or elsewhere. Why was it the case? The feeder is designed for 100 megawatts, but the heat supply company in České Budějovice only earmarked the network for covering at a maximum during winter months 80 megawatts. That's why the information that went to the general public was 70. Okay, thank you for clarifying that point. Okay, that's it. So thank you very much. And okay, we ran over our time. I mean, ran out of our time, but it's not that bad yet. I think it was a fairly interesting session. We heard about heat generation and consumption in France and in the Czech Republic, which is great. We're certainly interested in that topic. I want to thank Mr. Fiala, who hosted this session, all our speakers and listeners alike. And we will shift the beginning of our last session to 1:45. And before we go for lunch, I'll hand over the jars of honey.
Jako poslední přednášející a tady pan Fiala jako chairman. No, to je dobře, to je
A je dobré. Z minulého teda nevím, jak letošní, ale minulé je to dobré. Abych to protože jinak by tam bylo to ne, tohle ne. Pardon, 1,4. Jo, funguje to dobrý. No, ono to velké musí neznamenalo, že to tady napsalo, ale takže bude
jako tady na jeho ale jako ne jako No, samozřejmě, to jsme nedělali.
Kolik tam běžíme?
Jo,
Jste taky najít. No. Právě.
Když vyhodí, tak řekneš tak. No, oni ty body jsou. Tak řekneš, tak já vám nic neřeknu. Zatím jste tu sám. Ano. Já jenom
začnu nahánět teda.
Ano. Já mezi tím provedu, co provést musím. Ano. Fyziologická fakulta. Ano.
Raz, dva, tři, čtyři. Raz, dva, raz.
Dobrý den. Známe se. Grenoblu. Ale to bych jsem 30 let. Koris.
Ano.
Ano. Multifunkční simulátor.
Ano.
Sedla. To už si nebudete pamatovat.
Já si pamatuju.
Radima Mecu. Král? Jo, to byl zoufalý a to byl s elektránem. Potom byl Uravý tam byl. Ano, a od nás nám to udělal Radim Meca. Radim Meca.
Ano.
Radim Meca. Já jsem tam toho žežulu možná. No, a já jsem tam... Jo, Zouhar byl taky elektrárenský. No.
Já vás budu popohádat. Já to omlouvám.
Jo.
16.
Podivu moc netrčí, tak já děkuju.
Dámy a pánové, jsem rád, že aspoň někteří z vás už do
Ladies and
obědu.
gentlemen, I'm happy that at least some of you already finished their lunch. Hopefully everybody else will join you soon, but we have no time to waste. So let's move on to our next session. Now it's the session that will be moderated by Mr. Jiří Sedlak. And this session is an inherent part of nuclear power. We have a nuclear power plant, but we want to have it operational for some time to come. Thus, we need to pay close attention to what we call with an English acronym LTO, long-term operability. Before we begin, though, there is an urgent request to those of you who have been using interpretation not to forget to return them upon leaving. So that's just a friendly reminder. Thank you. Hopefully, those of you who are using the interpretation have their headsets on, so we don't need to translate it again. And now let's move to the final session of the day, of our two-day conference. For those of you who don't know what LTO stands for, it is the first apolitical, purely technical session, and it's not about lightweight heating oils. It's something else, and it is something that is not really translatable or translated. It's used worldwide. We don't really seem to have a relevant Czech acronym to call it. LTO stands for long-term operation of NPP. Even if we try to translate it directly, I wouldn't be able to show the whole scope of meaning of this term, because it is the entire lifetime or operability throughout the lifetime of the NPP based on the designed life cycle. We will talk about the events or activities that are connected with the maturity of such projects. And just to illustrate why it is such an important matter for us, NPP Dukovany has the maturity of 30 years. So as you can see in the table, since 2018, all 4 units are already in the LTO stage. Our session includes 4 presentations. The first one, it will be a presentation by Jan Vandrov from UJV Řeš. Then it will be Jan Bartak's presentation about leaks due to corrosion on the French example. Then we'll have the presentation by Miroslav Žamboch about pressurized tank of the reactor and LTO. And the final presentation, it will be mine, because my colleague had to leave for a business trip to France, and I will talk about the assessment of security and safety issues in the light of LTO. So we will kick off with Jan Vandrov's presentation, who is a mechanical engineer at the Technical University at Ostrava. He focuses on evaluating life cycles and maturity of NPP projects. 20 years of experience in this area, including 9 years in maturity management and LTO preparations in Temelín. Also, he gained a lot of experience and expertise in Ukrainian NPPs. He was an expert in 6 Salto missions and he's a very experienced professional in this area. Now the floor is yours.
Dobrý den, dámy a pánové. Moje přednáška bude
Welcome.
věnována řízení stárnutí jaderných
I will talk about aging management for NPPs, but also I want to focus on three separate areas. First, about LTO. Then I will talk about aging management. On a very specific example, I will show you how it is managed in different installations and facilities, so you know how it works. So, long-term operation, as Mr. Sedlak said, defines the operation of a designed installation depending on different types of reactors and types such as VVER. It's a design age or maturity is 30 years, and for BWR, it is generally 40 years. Here you can see the current age of various reactors in the world. X-axis shows us the age of reactors, Y-axis shows us the number of reactors, and you can see here very well that most of these reactors have the age of 30 years or more. So we can see that most of the operated reactors are already in the stage of LTO stage. So it means they're operating way beyond the designed and projected age, which is a very important prerequisite for our further presentation. Here we have some data from the International Atomic Agency and OECD data, where you see the cost of generating electricity using different sources. To the left, you see fossil fuels such as coal or gas. And here you see low emission sources, be it nuclear or renewables. And somewhere in between, you see the construction not of a new NPP, but an LTO, because new NPPs are more to the left. So the most viable economic option is to prolong as much as possible the operability of already existing sources. So it's unarguably the best, the most viable economically option to maintain or to keep alive all those NPPs who are already running. You see that when you're constructing a new NPP, the capexes and the cost will be enormous compared to prolonged LTO of existing sources. Let's have a look at the situation in the Czech Republic. NPP in Dukovany was commissioned in the late 1980s with the projected esteemed maturity of 30 years, but have been operating for 36, 38 years now. It might seem like an old NPP, but it's not the case. I'll show you why later on. Temelin was commissioned in 2000, 2002 with the maturity of 30 years, and it's still working within the limits of the designed age, which is 21 years now. Now, what are the approaches we can take to prolong the operability of NPPs? We have an American approach, which is prolonging the use, the operability and operation by 20 years, based on the laws and regulations in the US. It looks similar in Pax and Lovisha in VVER reactors. They have been prolonged. The operability has been prolonged by 20 years twice. So they will operate for 70 years, essentially. that has been already confirmed and approved. In France, the NPPs are evaluated and re-evaluated every 10 years. Here in the Czech Republic, we don't have any time limits or requirements. However, there are some conditions and terms that have to be met. Nevertheless, the license for operation does not include the time limit. When you are planning for LTO, it's mainly up to the decision of the operator and what is feasible. At the moment, ČEZ, as the operator, aims at having an LTO up to 60 years, also preparing for the prolonged operation up to 80 years in the end.
So, I've prepared an overview of the stages. You start with the technical and economic studies aimed at feasibility, which is intended to find out whether it is technically feasible and economically sound to extend the lifetime of the facility by another 20 or 30 years. It will always be advantageous economically unless prices have gone down by 30%, which is never the case. After that feasibility stage, a detailed assessment is provided and performed. My colleague, Mr. Sedlak, has already dealt with that. I will focus more on the aging management side of things. The facility needs to be under an aging management review. There are several parts of it. First of all, it's scoping. That's the selection and earmarking the borders, highlighting the borders, shall we say, the borderline between the different sets of equipment. That's hundreds of thousands of units, piping, armatures, pressure vessels, heat exchangers, the whole complete lot, the whole lot. An aging management review is then performed, and the nuclear power plant, even older ones, the life extension program doesn't start from zero, doesn't start from scratch. It usually needs to take these into consideration. Then TLEA revalidation. These are analyses of safety critical pieces of equipment, typically calculations that were usually done for life cycle management of these pieces of equipment for 30 years. They need to be recalculated for 60 years. And this is then submitted to the authority. And it's then up to the authority to decide whether this can be extended. Also, prior to that, there might be certain measures put in place in order to either introduce or improve the aging management programs. Now, as regards the nuclear facilities, nuclear installations, nuclear power plants, there is a Czech legislation framework as the law on nuclear energy, and then obviously this is based on respecting international recommendations from the International Atomic Energy Agency and other international bodies. We also benefit from the knowledge and experience and expertise gained in the aging management programs of other VVER units. mainly based on our contact with our Slovak counterparts, where they have the same reactors, and also based on the expertise collected from the Institute of Nuclear Research at Řeš near Prague, because we essentially develop our knowledge base in the same unit, as well as this is based on collecting expertise and experience and data from Ukraine, because there are 12 units of the VVER reactors. So our experience, the wealth of experience we have, comes from not only the Czech Republic, but also Slovakia, Ukraine, and elsewhere. Also, the Electric Power Research Institute is involved as a knowledge-based body. It's American by origin, but in fact, I believe the operators of at least half of the nuclear power plants operated in the world are associated in EPRI. And of course, they are also interested in aging management. So what are the programs of aging management for nuclear power plants in the Czech Republic? There are 4 types of programs that we have in place. The first group, I've taken the liberty of naming them plant programs. These are the programs that apply also to the regular power plants, electric power plants, for instance, such as control, operating controls, supervision and maintenance programs. And the thing you need to achieve is to make sure that all the mechanisms in place, all the programs in place, take good care and assessment of whatever mechanisms of fatigue there might be at work for the various units and pieces of equipment. Then there are specific aging maintenance programs that are focused on specific degradation mechanisms. For instance, low cycle fatigue, flow, induced corrosion, radiation, aging, TNR, etc., etc. The third type of aging management programs is focused on the most critical units or parts of the nuclear power plant: the reactor, steam generator, the main circulating pump, the main closing armatures, the core pipeline, etc., etc. And then also on certain parts that individually would not be that important, but there's a whole lot of them, and quite a few places are equipped with them, such as cables and armatures. And fourthly, there are aging management programs that are overarching or umbrella type of programs that might find that certain maintenance program is not sufficient for a particular type of component, for instance, due to an accelerated aging mechanism, and then these particular items will be moved over to the other side, other 3 types of programs. Now, what are the activity of the Institute of Nuclear Research at Řeš? We did scoping and aging management review, plus the TLAA, also the development and implementation of the aging management programs. Very often these are fatigue analyses and qualifications of electric equipment, which you can think of as simulated experiments or experiments in simulated environments, accelerated aging, etc., etc. And you test under the accelerated aging conditions whether these components remain functional, perhaps during an incident or an accident. And then we also develop our own programs of aging management. We are particularly interested and focused on the flow-induced corrosion, the aging management program for the pressure vessel of the reactor and the inside components of the reactor, cables, containment and armatures, etc., plus the piping. I will talk about this in more detail on the following slides. We also do the root cause analysis, for instance, for a burst weld or a crack. If there is an issue of this sort, the power plant company can send this to us, to the institute, and we can determine the root cause of the defect. We can suggest recommendation or measures that should be put in place in order to avoid this and prevent this kind of incidents and accidents. We use a database, essentially a database application that collects all the information, all the data, real-life operation data from the various testing and also data from real-life operations. And I'd like to tell you more about the aging management program for amateurs. Why did it come in existence in the first place? The majority of the amateurs for the two nuclear power plants in the Czech Republic were made in Czechoslovakia, in companies and plants that are no longer in existence. However, we were able to get from those companies good know-how and good equipment and good knowledge base in this area. The maintenance of these armatures was based on the recommendations from the manufacturers, and mainly, particularly focusing on the general overhauls, major overhauls once in 10 years, or perhaps replacement of the inner components of the armatures. TLAA generally were unavailable to us, meaning that the fatigue calculations were not available, which is something requested by standards and the regulators.
This is required by law and by regulator, and it applies to fittings, and it all had to be assessed that way. Since 1990s, we were evaluating fixtures and fittings according to seismic parameters, and during the preparation of life extension in Dukovany, we started calculating for the functional age of fittings. We are not doing these exercises to substitute regular O&M activities, but rather to prevent and predict possible corrosive and degradation processes, because what the producers and manufacturers suggested upon commission is insufficient if we are talking about an LTO. We provide these services for both Czech and PPs, and we do that for all fixtures that are relevant in terms of safety and security. These are some estimates, of course, but in Dukovany it is 26,000 pieces of fittings and 22,000 pieces in Temelin. These are vents with electric drives, with pneumatic drives, valves, safety valves, regulatory valves, control valves. And we look at not only integrity of the fittings, but also their functionality, whether they're able to operate. Now, these are other activities that we deliver when we are managing the aging of the fittings. We evaluate whether they are functional, whether the drives are properly set, so that the fitting opens or shuts under specific parameters, terms, and conditions. We also evaluate the wear and tear of various bodies, and we are monitoring degradation due to external conditions such as corrosion, thermal wear and tear, aging, erosion. We are also monitoring the number of cycles, how many times they're open, they're closed. Then we also monitor the history of operation and maintenance and the overall state and fitness. Now, the functionality, we evaluate various pieces of fittings with different drives. Well, I showed you on previous slides that we have a number of valves. These are large numbers in thousands, and we have to thus prioritize which are critical based on the qualification program and using the PSA, which tells us which of these particular pieces we should monitor because of their risk. So it's really crucial to make this analysis for all fittings. We use VAP software to do that, which is our internal program that we developed in the 1990s. At the time, we prepared it and developed it using the Westinghouse methodology that was prepared for the commissioning of Temelín, and it was prepared to be used both in Dukovany and Temelín. We also provide evaluation and assessment for the worsened conditions or decreased conditions. For example, when there is a decreased pressure to 80% of the installed pressure. We also check what happens when we have the switch configured incorrectly. With a tolerance of 10%, we are checking for the wear and tear of internal parts, whether they were all greased properly or whether there was no degradation because of the medium circulating inside the fittings. Here you see two examples on pictures from our software where we feed in proper parameters to have an evaluation of sorts. The wear and tear of the internal parts inside of fittings and of bodies. So this is something that we use instead of TLAA. We have many thousands of fittings, which would require more than 20,000 estimates of wear and tear for these fittings, which is a huge body of work. Thanks to this software, this program, we are able to avoid it. And first, we start with a screening process for all fittings, then applying certain criteria that are relevant to the wear and tear parameter. We evaluate and calculate the wear and tear for specified pieces only. The fittings that pass the screening process, which in Dukovany is 281 out of 26,000 fittings in this NPP. For those, we prepare MK evaluation and estimates. And based on that, we are able to define how advanced the wear and tear is. Monitoring the degradation due to internal conditions. Again, we don't apply it to all 26,000 pieces. Every year, what we do is we cut out a number of fittings for other reasons than aging management. We take them home, we cut them into pieces, we check them and decide whether the state they're in means something or is relevant to the state of the entire installation. Out of 26,000 pieces, it's roughly 10 types of these pieces And this is a relevant sample that we can use to decide what's the overall general state of fittings in the installation. Here you see on the picture the analysis of a valve. We also each year monitor whether there have been any failures reported for fittings. Whenever we have a report, we have to analyze or estimate whether the failure was due to aging. If so, then we have to prepare a more detailed analysis, which is then kept as records in our database, and it's all for the increased efficiency of the installation. So based on all these evaluations, we then put all these results into categories A, B, C, D. A, B means a good condition. C, D means there is some extra work that is required. For example, the shift in the drive or diagnostic activities during operation, one-off or repeated periodical checks and inspections. To finish off, key takeaways are LTO for NPPs is the most suitable way how to ensure low emission energy source. It's important to build small reactors and new units. However, the key effort should be, the major effort should be placed on prolonging life of existing units. Designed lifetime for NPPs is roughly 30 years, which is usually extended up to 60 years. Most of the reactors are roughly in half of their designed lifetime at the moment. We have a number of international activities aimed at preparing the reactors for the LTO of at least 60 years. So we have to ready ourselves for such extensions. And this has to be associated and accompanied by the aging management, including predicting the residual service life of an NPP. This helps us design a number of activities and operations that would ensure the LTO according to our requirements. Thank you for your attention.
Thank you for your presentation and also for being so punctual. He was right on time. I don't know if you heard me, so once again, I'd like to thank our colleague, Mr. Vondral, and also not just for his presentation, but also for being so punctual. Okay, one or two questions. I'd like to ask you one question that concerns the LTO of the steam generator at Dukovany. Can you say a few things about it? Well, what I can say about it is that we are not the main, I mean, talking about the Institute for Nuclear Research, we are not the main supplier of these services, but I do know that ČEZ has aging management program in place. Has been updated because the heat exchange piping is being exchanged at a faster rate than originally assumed, and I know that the steam generators are currently being cleaned to contribute to better maintenance. Is it something that ČEZ does, the LTO? I mean, does ČEZ take care of the approach and of the whole LTO program? Well, it is under the umbrella of ČEZ, and the calculations are also supplied as a support organization by the Institute of Applied Mechanics from Brno. We also do some research work and recommendations for the chemical side of things, the cleaning, etc. And Pramatom also works together with Skoda JS. Okay, thank you. And one more question, if I may, concerning the regulatory authorities. Is that Skoda, right? Yes. A banal question, perhaps. How many people do you need to have on your team to handle the aging management program? Because to me, it seems like a lot of work. At the institute that I work with, the whole division of integrity and technical engineering works on this. That's 170 people. Thank you. No problem. I wanted to ask you, while taking over the knowledge and expertise, do you also take over some knowledge from the Finns? I think the pressure vessels might not be up to our quality levels because the annealing has already been sort of developed to a better state-of-the-art level. They are scheduled to work for another 6 years or whatever. Do they have the same steam generators? Because let's say that the steam generators appear as the weakest link of the chain. Indeed. So is there any knowledge that we can take from that? And if they are going to run for 70 years, can we aspire to the same? To be frank with you, I don't know if they have the Russian steam generators or the one from Vítkovice or from some other supplier. I don't know. Generally speaking, about knowledge transfer and about the pressure vessel, yes, I can confirm that the knowledge they're collected over there is interesting to us and it's valuable because they've done annealing already. It's interesting to have access to this knowledge. They have also dummy elements in the active zone, not just doing the annealing stuff, but they have the dummy elements that absorb neutrons, thereby reducing the radiation exposure of the vessel. So this is also an interesting source of interest based on projects like IGAL or SALTO. There are various workshops at Lovisa. There was an interesting workshop that also we benefited from. Thank you. Thank you very much, Mr. Vandral. And if you don't mind, I'll give the jar of honey to our speaker just to make sure he doesn't leave without it. Our next speaker will be Dr. Barták. He's been here for several times. So introducing him is sort of reinventing the wheel. But just to let you know, this man has some 35 years of expertise and experience under his belt with modeling and international projects wherever you look, all over the globe. And primarily, he was the head of nuclear development programs at NG. So, over to you. Good afternoon once again. Here we go. Here it is. Several months ago, Mr. Zdebor and myself were pondering over what would be the interesting topic to the general public and to the professional public. And it was just around the period when there were some problems with cracking, corrosion under tension, under stress. So we thought it would be a good idea to put together a presentation and write up an article. My colleague and I, Dr. Kamarkat and myself published this article. I'm not going to quote it here, but if you're interested, I can tell you where to get access to it. Just to give you an idea about the nuclear French fleet, the French nuclear fleet. There are essentially three basic types of reactors. That's 900 megawatt reactors. These are the oldest ones. You can see the history. The blue ones will be the 900 megawatt reactors. Then the blue color, that's 1300 megawatts. There's 32 of the first type, 20 of the second type, and then the violet ones, the N4, 1440 megawatts, 4-loop reactors. That was interesting because the corrosion and cracking under stress only appeared in certain types of units and not the oldest ones. That was interesting. Now, generally, in what context did this happen? Of course, the French state has a very standardized fleet, and there's a whole lot of advantages that you can benefit from when you have a standardized fleet. But the problem is, if there is a problem, it is a problem that applies to the whole fleet, and you need to respond to it immediately. That's something that the authority, the supervisory authority, has been aware of, and EDF also knows about it. So you need to have a lot of capacity, a lot of backup solutions, so that if there is any problem of this sort, you need to handle it. You are able to handle that situation. But having said that, the energy policy of the French government in the recent years has been such that this was based on the assumption that the energy consumption would be going down. So they phased out 11 gigawatts of expedition output, Fessenheim, 2 units of 900 megawatts each, although it was fully capable of operating. The rest was fossil sources, particularly coal power plants, but they had been in operation for dozens or hundreds of hours in each year. So it was very good for the stability of the system and negligible in terms of emissions. So all of a sudden you have the situation in which you have no backup left, and all of a sudden you have this cracking problem. On top of that, there was this post-COVID environment where maintenance was not available or had been neglected, and France had to shut down 24 units, so 32 of them were actually in operation, and that was at the time when you paid 350 euros per megawatt hour in Europe. So the nuclear power sector missed its opportunity to show its resilience to the market at a time when it most needed the most, when it was needed the most. So France had to buy energy from Germany, and German-based coal power plants were running at full throttle. So it was a missed opportunity, unfortunately, for this reason.
This is, of course, a very unexpected issue that we identified first in N4 unit. It was, however, an extremely serious problem. We've noticed crackings on pipes near the pressurized vessel. So it was a huge safety risk, sorry. I have to see the slides. So we have to look at various characteristics. It has to be a serious defect and unexpected. So there are some phenomena that are well known, but here, when you have this global light water reactor fleet, has never seen any such issues among these thousands of reactors operating annually and globally. So we didn't have any experience of such defects. Another difficult problem was here that it's very difficult to detect using traditional UV methods that were applied systematically. But it's quite clear that this issue has occurred earlier and has been never detected. So not only was this difficult to detect, but also very difficult to fix because of its close location to the reactor. We are operating in a radiation environment, so the fixing and the repair is very complicated. So these are the things that can happen. This is the first lesson learned. There is never enough expertise, knowledge. We never know what can happen. I will briefly tell you about this slide. Under pressure corrosion, you probably know this phenomenon very well. There are three elements. There has to be a specific type of material, which is, for example, steel. There have to be chlorides in the environment, and we have to have stress in the material. So once these three phenomena meet, they result in SCC defects. What was surprising is that the chemical environment in the primary circuit is well known and very strictly monitored and has been for years. We don't have any chlorides in this chemical composition, so nobody expected that it might actually happen. If anybody is interested in details, you can have a look at the quoted article. Thermal oxidation, which increases with higher temperatures, and the cracks are extending a few millimeters a year, and it's very difficult to predict that they will show up. You only notice them once you see the SCC, once it has been there for years. We also, it is different from the thermal fatigue, because unlike in thermal fatigue, the cracks show later on, and even though we do some tests for thermal cracks, we are unable to detect SCCs. How did it happen? How did we get there? The first time we noticed it, it was the revision, the 10-year revision of the CVO unit. It was a pretty young NPP, 10 years in operation, and this is where we first detected on one of the elbows, one of the legs, this cracks, and it was by accident. We just simply did a more detailed inspection because it was a 10-year inspection review, and we started checking and reviewing records from previous inspections, and thus we found out that there were some signals, but they were not the ones that we'd expected. So we thought there were some that it was a transmission problem. Communication noises. So then we moved to the N4 NPP in shore, and again we started reviewing the records, and we realized that this was the same kind of noises that we actually experienced in the previous set of inspections. So in these 4 units, we managed to act pretty quickly. They were switched off. They were in downtime, and we did some further investigation only to find out that there were some SCCs present. The same thing we managed to detect in the 1300 megawatt reactor. These are not as modern as the further generation. It was in Penly 1, and it was sort of a cascade of problems. We started we started switching off the reactors because we had to inspect it. We are using a very well-qualified laboratory, EDF, that is tackling this issue. They established an international team of 15 experts that came to the conclusion that the only way to fix it is to cut it out and substitute with the new element. Even though we are developing new ways of non-destructive controls and inspections, we had to also prepare a special program for testing all 56 units. Also, we had to come up with analysis and conclusions and recommendations so that we would find out why this happened. The moment we thought we were on the safe side already, then earlier this year, we detected a similar issue in a different configuration, where we found out that these cracks were showing in reactors with welds that were twice fixed. And we found out that whenever we found out that these welds were fixed twice in the past, then always the cracks happened as well. What now? What is the current position based on the analysis that I just described? We can very clearly say that on the older reactors, you don't see the problem, meaning the reactors 900 megawatts and 1300 MWP4 in lines P'4 and N4 reactors. There are problems connected with residual heat, and you see that and the safety injection system, these are the problems that you encounter, and you can see it in the table where you have all the reactors indicated where the problems happened and in what area. This was residual heat and RIS. We also found out that the conditions inside the fittings and pipes are very important. If they are not stratified. So the main reason for it is not aging, but rather the geometry of the piping. With new reactors, with new units, the geometry changed, and this also affected the stress factor. And it's quite ironic, frankly speaking. It was supposed to improve the design, because for the older units, the first elbow was so close to the reactor that it was impossible to maintain. This is why they changed the design to facilitate and make the maintenance easier, with the result that in the system of all these elbows and arches, cracks started to occur, specifically in these two types of units.
You can see this in the picture here. This is the primary piping, and this is the emergency spraying system in the cold branch, and the problem appears here, primary circuit, and the elbow before the first armature, so you can't isolate it. This is the picture of the real-life situation, which is the elbow on the piping. This is where this phenomenon was observed. Based on that, EDF started off a pretty robust R&D program based on a 15-strong team, and they very quickly came up with this non-destructive testing method, quite a unique one. And they prepared a program of how to inspect not only this system, but also all the other components on the old 56 power plants, 56 reactors, I should say, where austenitic steel is used. Using the new method, the purpose of this exercise being to complete, or the mission being to complete the inspections before 2025. But the overall objective of combining this with regular shutdown periods after 10 years, so that you can do this during the regular maintenance and not, you don't have to shut down the reactors for a separate inspection. So what are the takeaways from this? Based on ASN president, the supervisory body of France, first of all, prudence and modesty. We need to be modest in that we understand that our knowledge and understanding is never complete. It evolves permanently, and you need to expect the unexpected, essentially. You need to be ready to embrace new and unknown things. You need to be ready to embrace them technically and also in terms of your staff competences. Operators should also adjust their prediction maintenance method in order to try to find the weak spots and find the unexpected, usually not omitting the inspections that you would normally not consider necessary. And he gave his respect to discovery of the unexpected SCC phenomena. And also this is a system that needs to be put in place to avoid any generic issues, generic failures. So, in summary, all the P4 and P/4 units are up and running because the piping has been cut and repaired. So France is again the biggest exporter of energy in Europe in a record time. That happened in October 2021. It's almost 2 years after, and the problem has been diagnosed. The root cause has been identified, the new non-destructive method based on ultrasound that will allow us to identify any problems of this sort on various piping and various components, allows us to do this by 2025 on all the 56 units. Thank you. Great. I should have also mentioned that all this information is public domain. EDF will probably not tell you all the things, but there was a parliamentary commission set up that follow the developments, and EDF had to report to this commission of the parliament. So I think it was pretty transparent. Thanks to Dr. Bartak for his very interesting, indeed, very interesting presentation. And if there are any questions, please go ahead. I'd like to thank you too for your paper. Can I just double check, have you ruled out the possibility that the base material was not the cause? I mean, chemical purity, etc., etc. You did say that the repeated weld repair was actually the root cause, right? There are two different mechanisms at play. That was in addition to that. And there are two parallel inspections, because you systemically check and double check all and inspect all the welds that have been repaired twice. But the primary problem in that elbow was not a problem related to a weld. That's something in addition to it. The chemical regime has been ruled out by EDF because it is so strictly controlled, that there's no way this could have happened. And also it would have to appear somewhere else. It's the geometry of the piping plus the thermal stratification. So based on this analysis, these are the two root causes, based on our analysis. Thank you. I wanted to ask you a question. So if this is something down to the geometry of the piping, when they were cutting the piping and putting the piece back, did they use the same geometry to avoid the problem again? As far as I know, they only replaced the elbow. So the overall geometry of that section of piping never changed. So I don't know. They might have an option to, they might have an opportunity to look at that, perhaps do something about the thermostratification, but I haven't heard that they've changed the design of that piping or the geometry of it. So I don't know. I haven't heard about it. On the EPRs, what they do is that, just to double checking that we can't have the same problem, can we? I don't know if we can generalize in this way, but the geometry on EPR is different yet. Thank you. One more question from me. The new NDT method that you mentioned, has it been applied elsewhere other than France? And have they had similar problems elsewhere than in France? Again, I'm not an expert on this particular issue, but if I have correct information and I understood well, this is a brand new method that uses something that technically was not possible 5 or 10 years ago, but is possible now, technically. So it's been approved by this panel of experts, and it's a new method that I don't think has been applied elsewhere, but you need to ask EDF directly. I'm thinking EDF, they have a nuclear power plant in the UK, so that could be interesting. Well, that's a different unit anyway that they have in the UK. Thanks again to Dr. Barták. And you get a jar of honey for every single paper you deliver here. So it's your honey week now. Not honeymoon, but honey week. Our third speaker, ladies and gentlemen, will be Miroslav Žamboch. He's from the same department, or the Division of Integrity and Technical Engineering. And he's also equipped with over 30 years of experience under his belt in material testing. And he's also involved in mechanical testing of steel and corrosion mechanisms. I believe there might be some contact points, overlaps with the presentation you had previously, and this will be about the pressure vessel of the reactor and the LTO. Over to you. Testing, testing. Ladies and gentlemen, I'd like to share with you a couple of slides on the topic of the pressure vessel of the reactor and the LTO after 30 years. It's a pretty simple structure. General information, a little bit about history, we can't do it without that. The purpose of operations and the degradation mechanisms and how we deal with them.
We have VBR reactors, which is water-cooled, water-moderated reactor, and pressure water reactors. Our reactors have a smaller diameter than others because we can transport them only using railway transportation, and the bigger ones require different types of transportation, which means that our reactors are subject to more degradation because the walls of the vessels are simply thinner. This means that the quality of the materials used to their production has to be much higher than in the Western countries. VVER life, service life is 30 years and the TNRs is 40 years service life designed. Here you can see the VVER 440 reactor from Dukovany. It is a vertical vessel that has a lot of rings, a number of rings inside, a number of various components that you can see. You see the rings and the bottom, and it is made of a special type of steel that includes a lining inside to provide sealing. And the bolts used are 140 times 6, so they are really, really big bolts. The diameter is roughly 3.5 meters, and it's more than 10 meters high. Temelín has bigger reactors with the capacity of 1,000 megawatts, and it's not in the LTO stage. It is operated in such a way so that it can be operated without any further expenses and costs. The construction is very similar. The only difference is that when you see feeding pipes here, these are 10-850, and we have 6 such in Dukovany, not 4. Here you can see the comparison of 2 reactors. You see that Dukovany is higher and thinner as compared to Dukovany. And you can see that it's been an evolutionary kind of development. We have VVERs that are much bigger than these. We have to be very well aware of what kind of materials have been used to construct these reactors, and you can see these basic materials that are more or less the same, and these are the steel alloys with a high composition of COs, and there are other components that you can see on the list. We were supposed to have a reactor of service life of 30-40 years. Now the new expectation is the life extension to 60 years or even 80. This is why we have to manage the aging processes of the MPP, so that the MPP is operational until the next revision, and then we can either decommission or prolong the life, extend the life, so that we know that we can rely on the generation of electricity for the given time period. We have conducted research and studies to identify the areas that might affect the life extension to further 60 or 80 years, and we found out that there were no such issues. And then we tried to map the areas where we had to work better and to use better grease, lubricants, so that we can ensure the life of 80 years. And this requires fantastic knowledge of materials and of greases and lubricants. Side note, all the analysis that we conducted showed that the operation of the pressurized vessel can be safe and secure, and we are preparing them for the service life of 8 years. Managing aging is all about the knowledge of the materials. For example, here you can see the ring that we are putting into the oil, and then we use extreme heat of up to 1000 degrees centigrade. We lower it to 687 to 20, and then we apply lubricants to the weldings, and then you see how we were welding the rings around the vessel with the heating applied at 300 and 400 degrees centigrade. It takes a lot of work. It is difficult to approach these and to get to these elements. Now, degradation mechanisms, which is thermal and radiation aging, which degrades and results in the wear of the materials. It changes and affects its chemical composition and properties. Low cycle wear and tear, this is something we cannot avoid, and this results in cracks. High cycle wear and tear, fatigue due to vibration on the main circulatory pumps. These are usually happening on the when there is a contact area between the reactor and the vessel. Also, mechanical damages that happen because of the work instructions not being followed. SCCs, so this is the corrosion times that we cannot exclude absolutely. And then regular corrosion, because the lining we have is only outside, and the steel that we're using is very susceptible to corrosion, and it's the same type used in the primary solution. To show you how dangerous the corrosion can be, Davies Best in 2002 reported an incident during regular inspection. Now, I did something I didn't want to do. Can I have some help, please? Thank you. So, you see the cover of the reactor Davies Best, and you see that there's only a few millimeters of the lining, and they were seeing some crystals appearing around the flange, and they checked it automatically, and they found out that according to the lid, there have been some leaks, and it was maintenance that was not properly done. Sir Vandross said that it's important to have an aging management program, which is part of the component program. You can see the structure of this program. We gather and collect all the data from various programs and processes on the NPP and uses it to generate the current information about the status and fitness of the reactor, and the results are the recommendations for further operation and maintenance activities. When you look at the sources of such information, you see different software functionalities, AMP, thermal and neutral and Brittleman monitoring, fatigue monitoring, water chemistry, AMP, maintenance, and AMP inspections, plus extra info sources that we use. Now let's have a look at the thermal and radiation aging. The material under pressure under these mechanisms loses their initial properties, plasticity, resilience, etc. These are degradation mechanisms that have to be monitored so that we know how they develop. We have to check whether the vessel is still integral, it's not cracking, and then we have to introduce the processes that would fix any potential cracks or the degenerative processes due to radiation of the that is affecting the material and its strength.
We need to demonstrate resilience to the thermal pressure shocks, that's the worst kind during the active zone. So hot reactor and cold water inside, which obviously provides for thermal tensions that can actually initiate sudden cracks. We can see that there are different types of mechanisms at play. The plateau then goes beyond the traditional values. The sudden cracking can actually happen after 1 to 3 to 5 years of radiation in the testing reactor. This is the practical side of it. This is what it looks like when it happens. So this is something that we want to avoid. The technical reality is shown on these two pictures. The first one is related to the Liberty class ship, which started to happen in the cold waters of the Atlantic when they swapped from riveting to welding. And the material was not of good quality. The initiators the initiations were really on the other side of the wells, and suddenly there were these bursts. And then this was an ammonia pressure vessel and other nitrogen-based fertilizers, and that's usually 22 megapascal. So these pressure vessels are really subject to high stress, and it can happen that this is what can happen as a result. So generally in the industry, any industry, sudden crack can be a problem, sudden fracture. The best way to handle this is to have evidence samples. So essentially what you do have is testing bodies, testing sections made of the very same material as the pressure vessel of the reactor vessel, and these are put straight into these same conditions. So the idea had to have been around in the 1960s or 70s, because the nuclear industry is a long-term industry and it's pretty conservative. During the history of the Dukovany operations, we've had several evidence samples, several programs. The evidence sample programs started off with a too high coefficient of radiation with insufficient number of the samples. Then our specialists created an additional program that covers 40 years of operation, and currently we have the extended evidence program that was generally designed for 60 years of operation. Now it's going to be extended to 80 years, and we've used all the tricks and tricks of the trade that we've learned in the past. This is the evidence sample method for Dukovany. You can see the chain, the individual boxes canned. This is the canal where actually channel for the evidence samples. You need to monitor the temperature, the influences that the samples receive, and this is based on the measurements done inside and outside the vessel. Now imagine you put something into the reactor and then you can't pull it out, so everything, there'll be a big problem. So you do check and double check and triple check. This is a sample from Temelin power plant. Is completely different, so that we have as much information as possible. This is what it looks like, where you put the containers in the pressure vessel in Temelín. These samples are monitoring the thermal and radiation aging, and the other ones, one slide up, are for thermal aging monitoring. I wanted to mention that the reactors are the Russian design, but they were in fact made in Skoda JS. We have better material and we have better information about manufacturing. In fact, there were 60 units of the 440 VVR and 3 units of the 1000 megawatts units. One was testing and 2 or 3 are installed at Temelín. And as far as I know, there was also a material set prepared for another set of units that never really materialized. These are the evidence samples, obviously are activated, so they are irradiated and they need to be tested in hot chambers, hot laboratories. And you can see the hot chambers. This is the window to the hot chambers, and the Sharpie test output then allows us to determine the properties that we need to determine. Now, something on brittleness. This is a calculation that is derived or measured from the initial state of the material before the reactor was put into operation, then the shift of the value, and then a safety coefficient, safety factor. So this tells you the brittleness temperature, the brittle temperature shift in time. So if you have a value for degradation of the material, you need to have a standard, so the maximum limit permissible for brittleness of the material, and this is based on the temperature. Is based on NTDS ASI, based on formerly applied standards, and the size of the crack depends on how good or bad are our non-destructive testing inspections. So safety operation is indeed guaranteed if the two values are in line with this set minimum value or maximum value. If there is a thermal pressure shock, you can think about a fracture of the main feeder pipe, for instance, of the 50 diameter, or perhaps sometimes it can happen that the emergency system can start to flow cold water into the hot reactor, so that kind of incident and accident. And then by analyzing the mixing flows, we can actually establish the calculated temperature on every single surface, and that, together with other calculations, goes into the structural properties calculation, which essentially will determine the propagation of the cracks and leading to a final integrity failure. This is the inside, the temperatures map on the inside in the 150 depth. This means that the main circulation piping with a diameter of 150 millimeters disintegrated. And this is the graph that shows the overall incident and failure. So this is how you measure, calculate and assess the resilience of the vessel against brittleness. Now, brittleness is not the only degradation mechanism. There is a low cycle fatigue. The Association of Mechanical Engineers of the Czech Republic puts a lot of knowledge into this. For the reactor, this had to be part of the documentation, but obviously this is something that is based in the 1970s state-of-the-art knowledge. So we decided to take a completely new exercise based on the NKP method, using the initial documents, using the exact geometry of the reactor pressure vessel, which wasn't sufficient in every single instance, but in Skoda they still have the original pressure vessel that they haven't removed.
Here you can see Mr. Pistora, who is an European format expert who is using various materials to make us precise measurements as possible. Not always is possible. Sometimes we have to use precise PC modeling. In order to do that, we had to do new fatigue calculation and including the aging management monitoring program. We were able to guarantee that if this reactor will be operated in the same way that it's supposed to be, then the service life can be prolonged up to the 60 or 80 years, regardless of the results of other evaluations. As far as the service life is concerned, we always have to monitor all the parameters that may affect it. If you see that any of such phenomena are developing and growing in a rapid manner, we have to always intervene. Here you can see an RPV from VVVR in Belarus, Astravets, where you can see that it slid out and fell down and dropped, even though there were no visible damages. Then we had to check it internally or through an imaging that you can see to the right. This is the surface of a console in the horizontal plane. After 35 years of operation, you can see some damage, minor damage. This was actually identified during regular reviews. SCCs have already been widely discussed. It's a very complex mechanism that is very difficult to predict. For me, I think it's even impossible. This is why it had to be monitored during various regular reviews and inspections. So we have to have RPVs designed in a way that will keep them integral and without any cracks in regular conditions of operation in the primary circuit. Of course, the geometry can be diverse, and not always we are able to avoid SCCs, but we've heard that in the previous intervention. This all requires control systems and monitoring during operation. We have a special program in place that was actually approved by the Czech Nuclear Regulatory Authority based on specific experience with operation and general global experience with operation of NPPs. This program tells us how, when, and based on what criteria we are supposed to control and check and monitor. This is what we use as the main guideline for our aging management activities. To finish off, please have a look at this RPV of skin at work. You can see how we are now. Another interesting example, when we are controlling or checking the internal surfaces of the reactor, and we are monitoring radiation damage evolving or developing in the reactor. And I think it's a very nice picture to finish off this presentation. We are looking after our reactors from every angle. We can ensure the service life of 60 years, and we have to keep on monitoring because it's a work of a large number of people from various areas of expertise, technical and academic. Thank you for your attention. Thank you, Mr. Žambok, for this presentation. Are there any questions? You mainly talked about steel, but there are also other specific materials, for example, in drives and that are controlling rods. There are special magnets, etc. Are there any special requirements regarding other types of materials? Yes, I did concentrate on the integrity of the reactor. As far as the drives are concerned and fuel cells or control rods, there is a separate program for aging management, and it's a separate category of monitoring. These are the elements that can be exchanged. There are spare parts available, so if they are subject to wear and tear, then we can exchange them for new elements, not only maintain and overhaul. All RPVs in Dukovany come from Škoda at V3, V4. Is it also Škoda? Because V1 and V2, they came from Russia, didn't they? Yes, I think so. As the moment they were decommissioned, I stopped caring about them, really. So I think you are right, because I remember that we actually took some parts from these decommissioned vessels, and there were some weldings that we did not know from our own manufacturing processes, though definitely that must have come from Russia. Thank you for your presentation. And now let's move to the final part of this session. Before you leave, please accept this token of gratitude. Honey. This is a presentation that we prepared with Mr. Hustiak and Holly. Mr. Holly was the one who was supposed to present it, but unfortunately he's in France, so I'll be stepping in. We have experience of 30 years in assessing safety of NPPs. We are very familiar with analysis. We are all from the same department of risk management. I would like to start with the LTO analysis for the safe operation. An NPP cannot be only maintained in a state that it was in upon commissioning, but it has to be continually improved. As with a car, with a vehicle, we have a service life for cars of roughly 8 to 10 years, mileage of 150,000 kilometers, that is the expectation. And throughout this entire service life, we not only change oil or grease or lubricants, but also we have some components and elements who are with service life much shorter. So it means we have to sometimes exchange them as well. For example, the exhaust pipe. If we apply the same to an NPP, it's as if we were getting an extra airbag that we were changing, or we were changing brakes for a cylindric, or if we applied a new anti-collision system to the car. The same goes for an NPP. We have an NPP that is somehow maturing, and it's getting matured and has to get better as opposed to what it was initially. This applies not only to this integral installations, but also to the softer sort of prerequisites, such as recommendations or regulations applicable to an MPP. This is something that we factor in when we are planning the service life of an MPP. But when we get to the LTO stage, the challenges seem to grow even bigger. As a result, the project, when we compare it to the initial phase, is changing and shifting. We have to assess and evaluate every single modification and change using safety measurements and analysis, so that we are sure that any and all modifications do not hinder the safety of the operation. So there are two basic types of analysis. Deterministic analysis. These, for example, include thermohydraulic evaluations, etc. The second group of analysis, these are PSAs. So these are probability analysis for safety, reliability analysis, etc. These are the two groups of analysis that do not compete with each other. They are more they supplement each other. It's not that we do one and forget the other. We have to conduct them both. I think we all know what a PSA is. I will, however, tell you in short what it is. A PSA is an acronym. It's an acronym used by the nuclear agency in the US, in Spain, everywhere where you can see the impact of the US, you will see a PSA, which is a probabilistic risk assessment. Not really safety. Risk was not very, a risk was not a favorite word to use in Europe. So instead we use PSA, which stands for security. This kind of analysis combines initiating events with the probability of the reaction on the unit and of security safeguards which are in place in order to contain the initiating event in the RPV, and it initiate an emergency mechanism and the consequence and the consequential sequence of events. There's a number of levels of PSA. The first level being CDF, which is a frequency damage of the active zone, which is the parameter mostly used for PSA. FDF, which is the frequency of fuel damage, and it affects not only the active zone, but also the fuel in the NSF pool. For the second level PSA, we are talking about LERF, which is the frequency of high timely leakage of fission products. So these are the basic analysis. There is a third level of PSA, but I wouldn't like to elaborate on that now because I think it's not something that has been properly developed yet. A PSA model combining two approaches visually, and they are very practically applicable. These are the trees of events. This is a typical school example of an event tree, where initially you see the loss of main feed water, which is initiating an initiating event, and then it triggers the sequence of event. It's an OT sequence. And the next function that happens is the reactor scram, emergency feed water depressurization, emergency core cooling follows, and this is followed by residual heat removal. So in the first line above, you see individual events in the sequence leading to the damage of corium. Just to illustrate what I was talking about, the second method used for the PSA modeling, these are failure trees where we are evaluating the probability of the failure of critical functionalities. This is one of such trees where you can see, this is one of thousands of pages of this model based on one of the signals that reported failure. So this is just a short introduction to the topic. The first level PSA includes a number of stages and phases, starting with the analysis of triggering events, the analysis of systems, reliability of the human factor, root cause analysis, outside and internal and external hazards, the sequences of emergency. There is a huge spectrum of the activities that need to be conducted in order to provide the PSA level 1 modeling. Initially, when we start the operation of an NPP, we have to calculate the initial risk level, and with time, when the NPP and the model is being fine-tuned, you either see the risk stagnating or to some extent decreasing. If the risk is increasing, then it should be reviewed, and possibly it requires also the approval from the regulatory authority. The expected decrease of the risk, however, can be stopped or increased. Not always increased risk is something that we don't want to see, because sometimes the model is being improved, it's gaining scope and scale, and it is being supplemented with various initiatives, triggering events that have not been seen before. For NPP management, it is a very problematic and frustrating thing, because initially, when in the 1980s we first came up with these activities and these exercises, we kind of knew radiation damage that we could expect and what that would mean for the NPP. We thought that, we never said that Dukovany will be best protected NPP in the world. But when we started investing in further analysis, the outcome was that the results were worse. But if you understand this process, then you know that the analysis which has more inputs, internal flooding, for example, then you get worse numbers. But on the other hand, we have a better picture of the situation in the NPP, and this is a better ground for us to make informed decisions about further activities.
And this is easy to publish then. Typically what happens is the introduction of external contributors, typically after Fukushima. So, apart from us talking about the overall number, we also follow the trends in the distribution of the contributors to the main risks in the operations. There needs to be harmony, and there should not be any major contributor to the risk. That is based on international standards. So over time, we develop and improve the project And over time, we achieve a reasonable balance between the risk contributors. As I've said already, the power plant goes through a number of modifications throughout its life cycle. And there are two reasons for it. It's to improve or increase the safety levels of operations and also to improve efficiency. Automatically, you anticipate that the risk level should be either going down or at least it should not go up. Talking about efficiency or effectiveness levels being increased, there could be a risk increase, but sometimes you prove that it's marginal increase in risk. Sometimes a efficiency, meaning economy, induced or motivated, economically motivated modification will allow you to achieve a better risk level, a lower risk level. Because you can introduce some safety features that would be otherwise not available. So that can happen too. When we talk about LTO, we're talking primarily about Dukovany, not Temelín. So what are the new features that we analyze using PSA? First, it was the installation of the third pump for the super emergency feeding and modernization of the control system. And there was a major global change that has been already covered at many different conferences, so there's no point in me reiterating that. I just want to say that it was not just rearming the nuclear power plant with, digital features instead of analog features, but it was really a major upgrade that had its impact and consequences for many factors and many areas of the nuclear power plant. There was also changes in how the nuclear power plant was being operated. We analyzed these as well. So new process, new principles, symptom-oriented emergency and accident-related rules for operation regime as well as for the shutdown regime. We also did what is known as the internal feedback, or from other, if you use the other nuclear power plants in operation in the country or elsewhere, it's called the external feedback. And obviously, you update the data on a periodical basis, for instance, to introduce the outcomes of new thermal dynamic analyses. So there are changes that improve the reliability rates of a component, and interestingly, these do not really influence the risk levels very much. But if there are any changes that reduce the potential for any subsequent or dependent failures, that usually is the area where you find a big impact on the risk levels involved. Then there are changes reducing the overforcing context, which essentially is the human error. So the probability of a human error, human failure, is being reduced. Then changes reducing the potential for initiation events. I believe that's something that is well handled at Dukovany. And then changes responding to outside or internal, external or internal threats, and the risk potential of those. Now I'd like to tell you about the changes to Dukovany that had a positive impact on the risk levels of operations. So LOCA, that was the drainage of the HCC2 boxes, the PG, and preventing leaks from the reactor. from the reactor shaft, to be precise, symptom-oriented procedures that reduced the risks by 40% and 25, that was during operation, regular operation, and 25 for non-performance operation, non-output operation. And implementation of the PAMS and the digital control system for the ESF actuation system, reinforcing the equipment on the section close to the reactor against steam leaks or feeder water leaks. And very recently, we introduced we have been introducing at Dukovany the various measures that respond to stress testing subsequently following the Fukushima-induced effort. It was a political and also economic impulse, I would say, when the thing at Fukushima happened. So this development there actually accelerated the introduction of these measures. Mobile facilities were also involved, like, for instance, the generators. Essentially, the whole unit can run on batteries, if you think of it. 6 kilovolts from the 110 kilovolts, and the standard diesel generators did not actually start up. So, and in that moment, you have just the battery. So station blackout, these batteries or station blackout diesels, these are the ones, 2 of these for each block, for each unit, and on thermal units, 1 per block, 1 per unit. It's been demonstrated during the Fukushima disaster that you do need electricity at a certain place. So apart from these generators, we also introduced mobile diesel generators. So you can see the firefighters' truck towing, flatbed truck with a mobile diesel generator of this sort. Actually, this is not from Dukovany. The photograph is not from Dukovany. At any rate, we can supply alternating current supply, but we need to also be able to control the supply. So here is where you connect up, you link up the mobile diesel generator. Here you have the connectors so that the electricity can get where you need it to. And in between is a mobile control unit. So you don't need any improvisation on that front. So there are procedures in place and what to do if anything of this sort happens. Another problem that happened at Fukushima, that occurred at Fukushima, was that a lot of parameters were just unknown. They were in the haze. The sensors were there, but the display units did not have power, and the sensors didn't have power. So the operators didn't really know what was going on under their hands. So there are mobile units that get connected to a panel of sensors, and they provide the minimum power supply and display of these parameters. The station blackout diesel generator reduced the overall risk from the external hazards by 60%, and the implementation of the mobile diesel generator reduced the frequency of a major leak by about 25%. Reinforcing the structures for extreme wind and snowfall, that turned out to be a major and surprisingly a rather complex development, where PSA played a role in earmarking the major points that needed to be reinforced. Typically the roof of the machine room, but if it collapses, there are certain areas where it wouldn't cause that much damage, but there are critical places where it would cause a lot of damage. Having said that, one would actually think that the critical part obviously would be the main thing, but thinking of it, the diesel generators, the roof of the building that houses the diesel generators turned out to be key, absolutely critical. And also the firefighters station, because the firefighter station needs to be up and running, and if their roof collapses and their equipment is simply in debris, they can't help. So there was a lot of tasks to think about and to put measures in place for. I've taken the liberty of selecting this picture. It's an additional external structure to reinforce the outside walls. Another measure involved the retention, in-vessel retention of the molten material. That's essentially this on this picture. And one feature that had been discussed way before the Fukushima disaster was the issue of the cooling towers. It's been known that cooling towers are only so much resilient to strong winds, and in terms of safety, the loss of tertiary circuit, it would not have that much of an impact on safety, but the other thing is the impact on the economic side of things. But at Dukovany, the problem was that the cooling towers were also used as the final absorbent unit of technical water that is used to cool down pumps and pipe locks. So if we lost that, we would not be able to remove heat in the long run. So that's why we made this, and it's the biggest change, and that is one that is seen pretty easily from the outside. This is when it was being built, when the facility was being built, just prior to completion. Now you can see the photograph after completion, and just to show what little giants these are, these are the two units side by side. At the Temelín nuclear power plant, they use the spray technology, but we didn't have enough space at Dukovany to do this, so we took a different path. All of these measures would be completely or almost completely useless if there were not procedures in place and rules how to apply them. Because you wouldn't really enjoy reading the stuff, so I took the liberty of picking this photograph to show what happens if there is a super emergency power supply needed. So they have the amateurs, they know what to do, they know where to connect the Fox, which is Fox 3, which is the mobile pump. They have the connection points tweaked so that this can be immediately connected to their equipment. There's no space and time for improvisation. And the third measure was the third pump for the pool that is used for storing spent fuel. The probabilistic safety assessment, PSA, has a lot of uses. Indeed, it is used for and throughout the life cycle, the whole life cycle of a nuclear power plant. But talking about LTO, I think they have a more specific meaning and significance. The best and most visible outcome of this is the tool that is used for monitoring risks. This is a training print screen from a training facility, an education facility. I won't go into too much detail, but it's just based on monitoring the operability or non-operability of the facility. The risk monitor shows the immediate changes in the risk levels. It can be anything from containment failure or whatever else. And obviously there is an effort to reduce the accumulated risks as well as reduce any peak time risk. There might be short time, but pretty major in terms of their size. Of course, PSA, using the probabilistic called accidents sequence events, that these are precursors of emergency sequences, that's really an important part of it. We've talked about the assessment of modifications and what-if analyses. These are the efforts that are put in place that already consider the effect of aging. Prioritization of control in terms of safety first approach, application related to the human factor engineering, validation of new and updated rules and procedures, staff training, operator training, improving the limits and conditions, risk-informed risk inspections, and that sort of thing. And to give you a summary, the probabilistic safety analysis is an integral part of an overall assessment of safety while operating a nuclear power plant. It is requested and required by Czech legislation. During the operation of a nuclear power plant, the PSA model and the way it is applied are being updated and improved so that they reflect the latest, the state of the art, and modification of the project and the real state of the equipment. It's called living PSA. If the lifetime is extended of a nuclear power plant beyond the designed life cycle, this is LTO, then the tasks for PSA are more demanding. Usually you can't have the data sets from the beginning and now, simply because the modeling exercises are completely different, not only by the quality, but also the in-depth and the scope. So, in fact, we are not operating, I mean, talking about ČEZ is not operating an old nuclear power plant. It's a power plant that is relatively new. Thank you for your attention. I'm happy to take your questions. I know you want to go home. Is it on? Thank you. That was an interesting one. I'd like to ask this question. Perhaps I'd like to ask something in addition to what you said. The stress tests were completed, then you did the assessment, then the program, let's say not upgrading or overhaul, but simply you implemented the outcomes of your analysis. Did you reevaluate this during the program? Well, essentially what we do is we upgrade and update on a continuous basis or annual basis the PSA program procedure. So it's not done at the end of the year, but there's a new report and a new study that is published annually. So the action plan for the implementation, it's not tied directly. So it's nothing special. So it's a regular PSA development program. Okay, thanks. There is one more question. Thank you. When you did the stress tests, I assume there would be some conclusions, and then the expert group would then calculate the super emergency accidents, I suppose. Is there any continuation of that effort? I'm not sure I can answer that question. Let me put it this way. I'm sure there were analyses done, and we conduct major accident analyses regularly. And I don't think they are specifically related to the post-stress testing measures. But you obviously work on a continuous basis on this heavy emergency, heavy accident analyses. I was really interested in hearing about the various sorts of risk. What about staffing or human error risk? With COVID, all of a sudden put us in a different situation. All of a sudden you can find that the whole team that is currently operating is sick. Do you consider these as well? Not specifically. There could be a lot of these cases, in fact. If the unit control room team cannot be exchanged, well, I think they would simply have to shut down the plant. I don't think we could actually analyze this and model the calculation. Well, we would probably come up to the conclusion that certain shift had to operate for another half shift time in extension to that, in addition to that. So you would actually increase the error rate probability. And I can't really imagine what kind of conclusion we could come up with for chess. I don't know. Other than that, it's a fairly interesting question, because yes, you are right. Even in Fukushima, people couldn't get to the places; they were simply inaccessible. So you remove debris and all the rest of it. But you know, a scenario in which the whole shift team would simply be down with some sort of sickness, some sort of problem, a health problem. It has to be sometimes, you know, something bordering on a catastrophe, on a disaster. There are procedures at chairs that go down to what you said. They have a replacement shift, a backup team. So it is something that we can deal with. They can deal with. One more. Hello, Wojciech Jansky. I'd like to ask you, when you do your PSA, it's for regular operations status and also for shutdown. Do you do it for every single type of activity that are based on the plan, or is it just done on a general scale? Let me answer this way. The model is handled for a typical shutdown procedure, but then you have the risk monitor, in order to find the individual weak points. And there's a number of switches where you can switch the shutdown mode, the shutdown procedure, in a particular way, depending on which of the components are non-operable. But with PSA, it's the average annual risk that we evaluate and assess. So it's when we do it, we use the typical average values with the non-operative side of things that obviously happen during a shutdown. But it's actually more detailed for the individual component parts of the shutdown process and procedure. All right, thank you. And I'd like to thank you for your presentation. This is from our bees. And in closing, ladies and gentlemen, I'd like to thank all of you, of course, the chairman in particular, and our speakers, but also, ladies and gentlemen, all of you who have stayed with us throughout the entire conference. It's Friday afternoon, and it's pleasing that it's not just the two of us talking, it's more than two. Thank you very much once again, and let me bring this two-day conference to a close. And I'll take the liberty of closing it by saying that, from my point of view, it's been great again. Really informative. We had an outstanding array of speakers and great presentations. And for many of us who have been in the business for their whole career, I believe we still could learn a lot, and I suppose even more so for those ones who are younger than me. So let's hope that this will be reflected in higher levels of knowledge, and I hope that this will contribute to the development of our sector. There is this exhibition, by the way, in the building of the mechanical faculty. That is the side event, and there will be the place where there will be the presentations for the secondary school students. I believe it was over 500 secondary school students that went to those presentations, and hopefully the seed was planted. We heard Professor Cizel and also other colleagues, Mr. Barta and others, the need for new engineers, and of course a host of other professions. That need is going to be huge in the years to come, and with our current way of supporting education in these spheres, we would not be able to match the demand, to cover the demand. So we hope that interest will be boosted, not only among the students, but also on the side of the government and politicians. Thanks again to all of you, and I declare the Nuclear Days of this year closed. Thank you very much.
Díky moc, pane doktore, díky, že jste vydržel. Pane kolego, já byl jeden od našich včel. Díky moc za Jirko, vám jsem med nedal, protože vám dávat med, to je jako nosit dní do lesa.
Děkuju.
Спасибо за возможность участвовать в вашей конференции. Рада была знакомству. Ждем вас в гости уже после победы. Спасибо. Все, до свидания. Спасибо.